sense-making, but the resulting ambiguity is rarely considered in the design of visual analytics systems. Avalanche forecasters rely on sparse and human-produced data to assess avalanche hazards, often resulting in ambiguous interpretations. We use simple glyphs and unit visualizations to specifically consider and support ambiguity in the avalanche forecaster's sense-making processes.
A testing environment for continuous color maps. Many other fields in the computer science do it, we should do it too. With our work, we introduced the approach of using test functions as a standard evaluation method. We present a test suite for continuous color maps implemented in the CCC tool. Adapt the task to your requirements at the interactive testing section and observe them at the testing evaluation section.
Entities and their changing relationships can be modeled more precisely as temporal hypergraphs, but hypergraph models are difficult to explore and refine. By leveraging domain-specific geometric deep learning models and a new multi-level hypergraph visualization, our technique allows for the direct integration of domain knowledge into the machine learning process. The multivariate hypergraph model structure can be analyzed on different abstraction levels. Simultaneously, experts can integrate their domain knowledge on the fly, and then explore the refined machine learning model.
We present Lyra 2, a system for designing interactive visualizations by demonstration. To design interactions in Lyra 2, users directly manipulate the visualization canvas. The system interprets demonstrations using heuristics and suggests possible interaction designs. We find that Lyra 2 enables rapid prototyping of an expressive range of interaction designs. We're excited to share this work with you.
Linking and brushing is very useful for interactive visual data exploration. Data-driven brushing tools are getting popular recently and achieve good results. For example, the Mahanoda-based brush and the CN-based brush. However,
okay, good morning. Welcome to the Paraview GUI by example at IEEE VIS 2020. We're excited to be here and go through some introductory Paraview material. We will all introduce ourselves, all of the tutors, presenters, in just a minute. But first, we want to make sure that everybody can get Paraview installed on their machine. We are going to be using Paraview 5.8.1. And the easiest way to find that, download it, and install it in the usual typical ways that you probably know how to do on your operating system is to go to paraview.org and click on download. Alternatively, you can go to paraview.org/download. And there's a couple of different ways to install on each machine. And before we finish this 15-minute introductory, we will come back to this slide and ask to ensure that everybody has been able to download Paraview and install it before we start the pre-recorded videos, which once we do that, it's going to be fast and furious, I guess. So we have another 14 minutes here in the introduction. But then at 8:15 sharp, we're going to start the pre-recorded videos. And all of us will be online ready to answer questions on the Discord channel or YouTube. And there will be short breaks. So the bold numbers at the end of each line item here tells us how many minutes we have for questions or discussion. So we have to be somewhat efficient and make sure to use the Discord and YouTube chat channels. But we will start out with three sections of using the GUI. After the break, we will have the third one, and then Ken Moreland will talk about effective color usage. And at 11:05, we will start with the advanced rendering techniques. I'm sorry, at 10:45, we will start with the advanced coloring techniques. There will be two sections of that. And in between, there won't be a lot of time for questions. So while that's moving forward, we should make sure to use the chat channels. So these are your presenters. I'm John Patchett. I'm from the Los Alamos National Laboratory, and I'm the production visualization lead. I've worked with Paraview for about 20 plus years. And this is a picture of me doing the only thing I did this year. I really like to go out and watch soccer games. And just before everything got locked down, my family and I drove to San Antonio, Texas, and watched, Austin, Texas, and watched the New Mexico United soccer team play against and lose, sadly, to San Antonio. But I will move on. Let Ken Moreland say something about himself.
Hi, I'm Kenneth Moreland. I work at Sandia National Laboratories. I've also been using Paraview for close to 20 years now, and have participated and helped lead a lot of the development of the software. And that's about it. So go on to Dan.
Hello, my name is Dan Lipsa. I work at Kittler for about 7 years. I am a developer for VTK and Paraview. Thank you.
Okay, and I guess we don't have Michael here this morning? He's in Europe,
yes.
I think.
Yes.
Okay. So Ethan.
Okay. Hi, I'm Ethan Stam. I'm also at Los Alamos National Laboratory, and I'm also on the production visualization team with John Patchett. I've been working with Paraview for about 3 years and helping with Lano's internal Paraview tutorials during that time. And unfortunately, this would have been my first in-person VIS conference, but due to circumstances, it's my first virtual VIS conference. So, yep.
Okay, so that's us. We're relatively friendly, so please make sure to ask questions and make this vibrant. And we will move on, and we're back to the getting Paraview installed. So the main reason for this first 15 minutes is to make sure that everybody has Paraview installed. And if you are out there in YouTube land, it would be nice to see a chat. Just tell us that you got Paraview installed and you're ready to go, or tell us you're downloading, or give us a status and let us know what's going on. And if you're having any problems, tell us that as well. And I will send a first chat. Hello. And I don't know if there's a chat, if we're supposed to use the chat on Zoom, or if we're just supposed to stick everything and ensure that we're using the chat on YouTube and Discord. You have 9 minutes to get Paraview installed. I'll drink my large cup of coffee. It is early on a Sunday morning, at least in the Western US, a little bit later in New York.
That is true, yes.
Hi there, I'm only seeing your slides as a small thumbnail with the schedule as the primary view here on the YouTube channel. So that's interesting. Sam, our technician, might be able to. how this goes down. The display that I'm showing is full screen on my Mac. The schedule is the primary view here on the YouTube channel. Yeah, I don't know.
Can people watch on Zoom as well?
I think it seems the preferred method is to be broadcast on YouTube.
Okay.
From the IEEE VIS conference.
Yeah.
So hopefully, so we have 6 minutes. Hopefully, when the videos start rolling, it'll go full screen for the videos that we've pre-recorded, and we already put our little faces in the corner. So hopefully that will work, and if not, we will actively start talking to the conference. So what the slide says, in case it's just the tiniest of thumbnails, is you should go to paraview.org. Our goal is to get you to get Paraview installed on your machine before the pre-recorded videos start rolling. And paraview.org, and click on download, and download for your operating system. Essentially, there's Mac, Linux, and Windows that are supported. If you can also go to GitHub and get the source and build it, which used to be how we always had to do it. But the binaries are excellent, and they have some data sets that come with them, some example data sets that you're going to want to have for the tutorial. And you can probably use 562. So 90% of what we do should work with 562, and maybe 100%. So if you have 562, that should be fine. There might be some slight nuances on where you click on things, but I think the capabilities are all there. And so, David, if you do have any problems and like a button's missing, you can just put that up in the chat, I guess, and say, hey, there's nothing to click on. But everything was tested with 581. Let's see. Section down is not Paraview. And we have 4 minutes left. Is there anybody out there that seems to be having a problem getting Paraview downloaded? Is the 1,000 people that are watching YouTube right now all hammering kitware servers and creating congestion? I was trying to come up with some good alternative operating systems that somebody might have that they were trying to install Paraview on, and other than some reasonable ones like other Unixes or something like that, Plan 9, anything we're not supporting properly. Has anything been fixed in regards to the small thumbnail for the slide? Or is it still that way? No. That might just be the way it going to roll. So in terms of the live presentation, we have very little of it and very few words. So this is as worse as it gets. And since there's already a schedule, my previous slide was probably useless since I was showing a small, or I guess the conference was showing a small schedule and then we showed a schedule. You have 2 minutes left to get Paraview installed. And I wore my Paraview shirt for this too, which is, this is the first time I've worn it. Very exciting. Already got a spot on it though. Okay. Okay, so we're told that the issue should be fixed, and we will be starting the first part of the pre-recorded tutorial in probably 30 seconds or so. And feel free to ask questions, and we will be monitoring the chat channels through that time. And we're going to start now. So hello, this is Paraview by Example by John Patchett and
Ethan Stam.
And we are going to introduce you to the Paraview GUI. And the first step in getting to the Paraview GUI is to get it launched. And you know, we have Macs, Windows, and Linux boxes. On my Mac, I usually launch it just by double-clicking the icon or going to Applications and double-clicking the icon. But on my Linux box, I usually just give a fully qualified path to the Paraview executable. And then on the, well, my email will be coming in during this process, I guess. And then on a Windows box, how do we do this on a Windows box? Double click the icon.
On a Windows box, I normally just navigate to the folder and double click on the executable from the file browser.
Okay. And, you know, one of the nice things, if you launch it from a command line, it's a very convenient way to capture error output and stuff like that. Now, there are other executables like PV Batch, PV Server, and PV Python that you might see in the binary directory. And those are part of Paraview, but they're not part of the Paraview GUI. And we hopefully will have a little bit of time to talk about those during this tutorial. So once you get the Paraview GUI launched, you'll see that there are some components to it, right? There's a menu bar with all of the normal things you might see in a menu bar with, like, you know, file and edit, view, sources. And we'll talk about most of those. Then there's this set of toolbars. And the toolbars are essentially things that you could probably get to through the menu bar, not completely, but they're really convenience functions, things that you might use frequently. The pipeline browser shows us the all of the elements of a visualization pipeline that we're assembling using Paraview. And then that's linked to the properties dockable panel. And the properties panel, you know, whenever you click on something in the pipeline browser, it will update information in the properties panel and likewise in the information panel, which we'll talk more about later. And then, of course, the render view is where the picture shows up that you're managing. And also notice there's a bunch of icons across the top of the render view panel that are associated with that particular render view. And let's make sure I got a Paraview running here. And I'm going to reset that session. And so here's a blank Paraview that is just like it's just been fired up, and you can see all of these things. On Linux, I actually have the file menu right at the top of the window. Have I missed anything?
No. I would just say that those dockable panels, you can undock them and move them around and configure the GUI however you like. So if you want the properties to be its own separate thing, you can do that.
Okay. So the next step is opening files. And there's really 4 ways to open a file. The first 3 are nominally the same. They get you to open file dialog, and then we can drag and drop a file into Paraview. I will show you those ways now. If you go File, Open, you'll get an Open File dialog. And it's just like any other file open dialog, basically, right? Except for Paraview will come with this examples directory that's kind of firmly placed in the upper left-hand corner of the window, which comes to some example data sets that exist. And so I can just click on that and click OK and click Apply, and we'll get that opened. I'm going to delete that. I can get to that exact same menu by going Open with the icon. And I can double click it and got some QT error on my box here. We can just close that probably. It's not going to cause us any problems. And here I'm going to kill Paraview and actually restart it. You can see me get rid of our QT error. And then, let's see, so we did the file open, did the open there. Oh, and we can also do a Control O. On Linux, it's Control O, and Ethan,
no, on Windows, it's also Control O, and on Apple, it's Command O.
Okay. And then finally, my favorite, I can just simply drag and drop a data file into Paraview, and it'll show up, and life will be grand. I can click Apply, and I don't have to, if I've navigated through some, operating system GUI file system browser, I can just, if I see the file I want, I don't have to re-navigate, so that's kind of convenient. Okay, so I'm going to delete that guy, come back here, and so now you should be able to open a file. We showed you the example, where the examples are, and we'll talk a little more about the example data sets. Do you want to talk about those, Ethan?
Yeah, sure. So Paraview comes with these 3 example data sets whenever you go and download Paraview from paraview.org. These 3 data sets are can.ex2, disk.ref.ex2, and headsq.bti. The can and the disk are both in X's file format. The can is 43 time steps of a can being crushed by a brick, which we'll see how to cycle through that time later on. Disk.ref is a single time step up from a fluid dynamics simulation, and you can do a lot of cool stuff with that to show vectors and some interesting things there. And the third one is headsq.vti, which is VTK image data, and that's a 3D scan of a human head. It's cool to do some volume rendering with that one.
Okay, and I will open those guys up real quick. And so any binary release of Paraview you should be able to do this, right? So you go Open and just click on Examples. And so I already opened the can.exe2. Here, if we open disk.ref and click Apply, it looks like a nice cylindery thing. I'm going to delete that and open headsq.ti, and that just gives us outline frame. This might be worth a point of showing that we could there's a representation aspect here, and we'll talk a lot more about that soon. But here we could turn that into a surface, and we could color it by the scalar or whatever scalar fields are available, and we can kind of see there's just a solid block of data, and we'll explore more of that later.
Okay. So now you know that there are these three example data sets that come with Paraview, and if you have Paraview, you probably have these, and you can open them and explore them, and we'll help you figure out how to explore those as we go through this tutorial. So one of the first important things is to understand the Apply Data button. So in the Properties panel, there's this Apply Data, and the general idea of that is, since Paraview is designed to work with large data, you don't want it to just automatically do things for you, because if you click something in the GUI and you didn't mean to, and it happens to be an operation that takes, you know, minutes and tens of minutes or an hour, you just really want to make sure that, like, oh, I didn't accidentally click on something and then it went out to lunch or something. So what the Apply button does, it allows you to make changes in the interface, and then once you're done, this Apply button will be ungrayed out, will be active in the Properties panel, and you just have to click it. And there is a way to have it auto apply changes, and that's the apply changes parameters automatically, or apply changes to parameters automatically, and I will show you that real quick. And so that button is right here. It is about the 7th button over. Is that right? So, and from the left, and if you click on that, you can see that it kind of like sticks, and you can unclick it. So if you stick it, drag and drop can, it automatically loads the can. Then, you know, there's this selecting variables, which will do more. You start doing stuff, it just automatically updates as soon as you click on the element in the GUI that forces something to happen in Paraview. It will automatically do it. And so for small data sets, that's perfectly acceptable. And for everything we're doing here today, I think you could actually turn on the apply changes automatically, but I am not going to leave that turned on. And I'm going to delete that again. We'll come back here. Anything else to say about the apply data?
For me, generally, it's not something that I use ever, just because I don't want my Paraview to get locked up processing something that takes a long amount of time. So I would recommend not using it, but like John said, for small data sets, it's definitely usable.
Okay. So reset session. So reset session is an ability to, you can go in and do a whole bunch of stuff in Paraview, and say you want to just be done, you've experimented, and you just want it to be just like you stopped Paraview and restarted Paraview. So the reset session button, which is this one is the 5th one over from the left on the very top row of the toolbars, and which is by default because the toolbars are also configurable. So say we have done something with the can, we select all the variables, we click apply, and now I got that, and I go, oh, gee, I really want to go do something else. And I can just click on the reset session button. It will ask you if you're sure you want to do this, which is actually a good thing, because it could be difficult if, like, there was one button that could just kind of wipe out your current session state. So I do that, and this is kind of like having just a brand new, fresh Paraview. And Ethan, am I missing something here? You got the client server. How does it behave in the client server space?
Right. Yeah. So the reason that what I would think the reason the reset session even exists is because the common use case for Paraview is running in a client server and connecting to an HPC and running in parallel on one of the HPC's nodes. So reset session allows you to start from scratch, just wipe everything away without needing to completely redo that whole connection process.
So if I click reset session while I'm in a client server mode, it retains the client server mode. It doesn't reset my connection. Okay.
Right.
Okay, so Then within Paraview, in addition to these 3 data sets that come with Paraview, there are a large number of sources that are essentially synthetic data sets that you can use, and they represent a large number of the types of data sets that Paraview can deal with. And so frequently, I use, you go to sources, alphabetical will list them all, and I go down and I use wavelet a lot. And so of course you got to click the apply button, and I already showed you the representation can be surface, and then I could also change the color to RT data. So if you don't know, or if you want to learn about all of these sources, I think some of them have really nice explanatory names and some don't. But there's this little question mark that's in the properties panel. And for everything that you can load and get into the pipeline browser, like all the filters and all the sources, you can always click on this question mark, and it will come up and give you a summary and some useful information about that filter or source. And I encourage you later to go through a number of these sources and just click on them and explore them and figure out what they are and how you might be able to use them. We'll also load a sphere source because we can. Oh, but I can't see anything, so I'm gonna let me delete my wavelet. Maybe my sphere was in the middle. Oh, and now I have this little tiny sphere. I'm just gonna reset my camera here. Oh, and there's a sphere. And then of course there's options. Also, a really key element in these is in the properties panel, there's this little gearbox that gives you some advanced settings that you might not get if you don't click the gear. So if you don't see what you're looking for, definitely try and click the gear. Okay, so I'm going to delete this sphere. Oh, and then we got the so here we have whatever is highlighted in the pipeline, remember, is what shows up in the properties information. So we could say increase the resolution of the sphere a little bit and make it look smoother. We could even make some fraction of a smear. So what you can do is just go and explore this. Look at the parameters, and again, if you want to know more about like what you can do and what the controls are, click on that little question mark in the properties panel, and it will tell you more. Do we have
and one thing to add there, the difference between a source and a data set is the sources aren't living on your disk. These are all data, well, they're data that's generated on the fly, and you can go through and change the parameters and kind of experiment with the properties panel and learn how the properties panel works in general.
Okay. So we also have a number of example visualizations, and I think that Sandia National Laboratories worked really hard to get these in there. And so what I'm going to do is I'm going to reset my session. And all of these example visualizations are in the help menu, and you go help example visualizations, and it comes up with this nice box. This is something you can do with that wavelet source that I showed earlier, that you can also load and go by sources, and you can see that they have a couple of filters, and you can see everything that's happened to it in the pipeline here, right? So you got a wavelet, and then they made a contour on the wavelet with 3 contour values. Then there was this extract subset, and we will talk about all these things. But you can explore these data sets pretty easily. You reset the session. You go, oh, I looked at that. That was cool. Go back to example visualizations. They have one with the can. This is a nice place too to just show you. You probably saw these VCR controls across the top, and since the can is a time series, we can watch that can crush, which I find very gratifying at times. Okay.
Also to note real quickly is the eyeballs next to each element in the properties panel. So you can toggle which element is hidden or shown by clicking that eyeball.
Oh, yeah. And you notice that once I click that eyeball for this particular filter, it shows up with, it resets some aspects of the properties pane, which was to actually show the cut plane that was being used. And so when I just have to uncheck that again to get back to that visualization the way it was. Okay. Example visualizations, help example visualization. So now on to the select data variables. So whenever you load a data set, the data set typically has a number of variables with it, but you can control which variables get loaded. So if you have a data set with like 150 variables, maybe you only need to read 2 or 3 of them, and maybe if you read all 150, it would be too much memory consumption and stuff like that, and take a long time. So whenever you try to load a data set, so I'll load can.exe2 here, and say I want to load just 3 variables, I can click apply, and I will have loaded these 3 variables, which it's worth noting that you can see those in the information tab. You can see what actually ends up getting loaded here. And if I want to just check them all, I go back and look at the information tab and see that they're all there. Let's see, and there was something about the memory.
Yeah, you can see, so for example, John, if you can just load displacement.
Oh, so go to properties, and we just want to load displacement. So I'm going to uncheck all the variables and then just load displacement and click apply.
And then go over to the information panel, and there's a little area called statistics, which will show you useful things, the number of cells, the number of points, what type of data set it is, and how much memory is being used. So right now it's hard for me to see. It's 0.88.
Yep.
And then if we go back and load everything, you should see that jump back up to 1.7, I believe.
Okay. Yep, 1.7 megabytes. So yeah, and that brings up another interesting thing is one of the panels that you have access to. And so if you go view, and we can look at the memory inspector. So the memory inspector is really convenient because it'll tell you, so my machine here, Ganymede, has is using 3.74 gigabytes, which is 11% of my system's memory. But Paraview is only using 491 megabytes. Now, what's really cool is if you're in a client-server connection where you have your client running on your desktop and a parallel distributed memory set of Paraview servers running on the supercomputer, you'll be able to see each one of the nodes in your job and how much memory each node is using. So if everything is distributed really nicely, everything will be equal, but sometimes it's not, and it's important to know, because if you try to do the next activity and you got process 0 or 7 or whatever that's has a lot more memory usage than the others, you may run out of memory on that one processor and your system will crash. And so managing, figuring out which nodes are using how much memory and how much memory your client's using, especially with big scientific data, it's an important thing. So know that the memory inspector's there, and if you're running into problems like that, find the memory inspector and kind of investigate what's going on. As you build your visualization pipelines, you can watch the memory usage grow. Let's see. Interact with the 3D view. So you probably figured some of this out already if you fired up Paraview. And here I'm just going to get rid of the memory inspector now, so we got a nice big render view again. And so if you left click and move your mouse around, the 3D view as you move around. If you middle click, it translates. And if you right click, it will zoom in and out. And you can manage these things too, especially some of you are probably using like a Mac laptop or something. So try hitting like, you know, the control button and then just touch the pad and move your finger around. Hit the option button and do the same. On my Linux box, if I hit the option button or the Windows Meta key on my Microsoft keyboard here, it will move the whole window around. So it doesn't work well for me, but it'll probably work well for you on your Mac. And the place to go find these key bindings, by the way, is in edit settings, and I believe on the Mac that is
Preferences.
Edit preferences. And so if you go to edit settings or preferences and click on the camera tab, it shows you what all of the motions options are, and then, you know, what they are. So a left button's a rotate, pan, zoom, and then a shift plus is a roll, and rotate and pan. And then you can also change those and customize those. And note too that, you know, we have the 3D interactions, but there's also a 2D interaction option here, which is a kind of a separate kind of interaction style. And I will show you that now. So we have or actually I think we have another, note the 3D button up here on the render view. So this is associated with the render view. It's a little icon that says 3D. Oddly, if you click the 3D button, it changes it to 2D. And so then if you left click and move around, you just translate the data set. You translate the camera. Let's see, and then you can just click 2D to go back to 3D.
Quick note on that: if you open a 2D data set, then Paraview will figure that out on its own and start the render view in a 2D mode.
Yeah. And so sometimes that's confusing if you end up with just a single plane and you're like, wait a minute, I always do 3D stuff and now it's not working. Okay, so you know the 3D button is important and the 2D button is important, and knowing that there's two different interaction modes depending on which one you're in, and you can see those interaction modes through edit and settings or edit preferences depending on your operating system. Okay, and so interact with 2D view. We did that. We're going to load the disk source and 2D, 3D, and have you move that around. We're going to do that during the interactive session in just a bit. So applying a color map to a variable and a representation. So we have an active variable controls toolbar and a representation toolbar. I kind of keyed you guys into this before, but so right now you can see that we have loaded can because I got my pipeline browser. Look at my properties. I got a bunch of variables associated with it, and what we have here is I can represent that in a lot of different ways, right? So we'll just go from the beginning. I got 3D glyphs, and so at every point in this data set, it's given me a glyph. Little vector arrow, I guess. Feature edges. So this just shows us, you know, the edges of the surface. The outline, which kind of shows us the extents of the surface in axis-aligned ways. Point Gaussian, which I'm not 100% certain what that does.
Point Gaussian just shows you the points, but they're not. I don't know how to explain it. They're not rendered as a single point, so they're not always going to be a single pixel. As you zoom in, those points are also going to get bigger, which is in contrast to the point representation.
Oh, okay. But this is on points as well, so it's a representation, some geometry that's added to every point. And then we have points, so this is the point, I see. So here this is just little specks, specks in space. And then we got the surface, which we already know and love. surface with edges. And so this is very convenient because, like on the can, it makes it really easy to see that the can is, you know, 3 nodes deep, 3 cells deep, and you can just see kind of what the surface. It's just the surface, but then on the surface also showing where all the cells are. Thank you. I forgot the word cells. And then I'm not going to do volume rendering right now. Oh, well, I will. But then I'll just do the wireframe too. So you can also see these cells in the wireframe, and sometimes that's complicated to look at. But the wireframe is often useful.
Maybe you could open the head to do volume rendering.
Oh yeah. So well, let me start with this one because you know we go and I go, oh, I turned on volume rendering and I don't see anything, right? But that's because really what I really need is what is that, acceleration? I still don't see anything, and that's kind of interesting. And I, you know, I'm like, huh. But remember, the can is a time series data set, and really there's no data to speak of early on in the can because, you know, some of it is like displacement, for instance. So here we're looking at displacement, and if there hasn't been any displacement or it's 0, oftentimes the volume rendering transfer functions don't show you anything. So yeah, let's go ahead and load the head. So I'm going to reset my session. Yes, and I presume the head should give me a decent volume rendering right up front. Yep, and there we go. So moving back, that's representation, and then we also have the color by box here, right? So the head only has one thing to color by. You saw like the can had numerous things, and so if you want to color by a different scalar field, this is where you choose that. Okay. Back to this. Oh, and very little about colors and active variable control. So we will talk a lot more about colors in this tutorial, but we're just going to get you the bare minimum started here. So in the active variables controls, let's see, and the active camera controls. Well, let's go to active variables. So let's not use the head for this. Let's go back to the can. I don't know what'll happen with the head, which might be interesting, but since we're recording this, we'd have to go and like edit the video. Let's see. So what I have here is we're coloring by blocks, but let's color by. Let me get all my variables in. So let's color by displacement, and of course, right at the beginning, everything's kind of 0. And you see that my color bar goes from 0 to something to the -38, which is basically 0. And then so we're going to move forward a couple time steps, and you see now it's not 0, so everything's up off the top. And so one of the important things is to be able to rescale data to range. And so what this will do is it'll take all the data that's in the time step and find the min and max and rescale your color bar and your color map to go from the minimum value to the maximum value. And then the rescale the custom data range would allow me to say, well, you know, I really want it to go from 1 to 3, and I don't care about those extreme scalar values. And so this allows you to just do some adjustments of the mins and maxes of the color system. But then, you know, the time, and we just kind of saw this when we opened the can data set, is that, you know, when you start and the range of scalar values on time step 0 is highly unlikely to be the same range of scalar values at time step n, or the final time step. And so, and you don't really want, if you're making a movie or something going through all the time steps, you don't really want to, change your color map at every time step. You can, but that's difficult to follow, and then it's just a difficult problem. So one of the things that you can do is hit this button, which will go out and read all of the time steps and rescale to the min and max of all the time steps. And you'll actually get this warning here because, if you have a terabyte of data out on disk and you tell it to do this could be one of those operations that takes a really long time. Hey, read all of my data, which could be, 1,000 time steps with 1,000 files per time step. And you may even run out of your supercomputing time allocation while you're doing it. So, but we're just gonna do that here because it works out pretty quickly on the small data. And now if we go through, we have this consistent color map, and you can see that it the color map is fixed between the min and max of all time steps. Let's see, and then the rescale to data range is kind of an interesting one because that's the visible data range. So if I zoom in on something and I click that guy, it'll just rescale the color map to the min and max of all of the cells that are visible in my view. Let's see, do we need to, there is this edit color map, and we're gonna have a whole section, I think, on the edit color map. And if you click on that, you get this color map editor, which I will pull out and make bigger so that we can see that. And you can see that there's a lot of things you can do. And if you want to mess around with this before we get there, you can click on these things and move them around. You really can't break anything. Well, it's hard to break stuff. And then there's a whole bunch of options over here, which, all of the options we just saw, which is like rescale to data range, and all of these things are also available in the color map editor itself. Okay. Anything we missing on the active variable controls? Okay.
Oh, did you show the magnitude components?
Oh yeah. So if we do, if you do want to color by something that's a vector, right, which is I believe acceleration is a vector, and the way that I remind myself on whether something's a vector or not, if it's not clear, is I can go look at the information tab in the data arrays, and I see that acceleration here has 1, 2, 3 components to a vector, and so that's likely my vector, right? So if you pick a vector, you will get some options in to color, like how do you want Paraview to deal with the vector, right? In terms of a color map. And so you can do magnitude, you can do the X component, the Y component, or the Z component. Okay. Animate the data. We already saw a lot about the animation. The can is convenient for that because it's a time series example data set. And yeah, for those who never had VCRs in their lives, is that you, Ethan?
Nope, I had one.
You did have a VCR. So you can, you can go all the way back to the beginning, and you can play. And here, let me get I'm going to zoom out a little bit, and I'm going to color by displacement, I guess. And I want to go back to the beginning, so I hit that far left one. I want to play. I hit the play button. I want to go back. I want to step forward one at a time, and so I can like really handily control the time stepping. And I just want to go to the end. And then this button here just allows you to do a loop. So if you just want to, sit in your office and ogle at your beautiful visualization, your masterpiece, you can do that over and over again. Every once in a while, I find somebody doing this. Let's see. The other thing to note here is the time sequence. So as you play through time, if everything is good in the world, your simulated time will show up in this time box And then the box right next to it will show you the time index from your simulation. So if you're making a a VTK data set, that's really, you're trying to figure out one of the key elements for dealing with time is ensuring that Paraview understands what the simulated time is and what the time index is. Otherwise, you'll just get time index, and time index will equal time. Let's see. Yeah, so camera controls are super convenient because you saw me use one of these already, which was, hey, I lost my data over here. I just want it back, and I can reset the camera, right? And if you mouse over these things, by the way, they will just show up and kind of give you a little bit of a hint as to what's going on. And so, like, this guy is zoomed to data. It feels like reset, but it changes depending on what the extents of the data are. This is zoom to box, so if you click on that and you highlight it, it will zoom to write exactly what you made. But then we have all of these 6 axis aligned buttons, which essentially put your data in view and put it in an axis aligned way. So you can just click on all those guys. And then, of course, turn it 90 and turn it back 90 on the axis that you're on. And you can click these things. They're fun. It helps you to get back to a constant state. Normally, when I'm working on a complicated visualization that maybe is slow to move and interact with, I kind of figure out which one of these buttons that I like the most, and I click on that one. Let's see. And while we're here next to it, and I don't know if we're getting to this, oftentimes I can recognize visualizations that were made by Paraview because they have these little axes here that are clearly Paraview axes, and so you can simply get rid of those by clicking on that. So if you want to make a pretty picture for the boss or the report cover, and you're not caring about what the orientation is at some moment, you can turn that off. Also, making pretty visualizations, you can move the color bar simply by clicking on it and moving it. Okay. We covered all the camera controls toolbars. And then, so, some resources for using and learning Paraview. Paraview.org is a really good place to start. The Paraview guide, and you can just Google these things too, right? Paraview guide, the Paraview GUI help, which I have another slide on. And then we have, you can Google file formats PDF if you're, struggling, you have your data, you're like, man, I really want to see my data in Paraview, but I don't have the right format, but I have the skills to, maybe change formats, or, I understand, that this is my list of points and this is my list of cells, and, and file formats.pdf will take you a really long way to figuring out how to get yourself into reading some Paraview data. And then, of course, just straight up Google. Let's see. Oh, and there's also, you can discourse. What do we want to say about discourse?
Yeah. So if you go through some of these things and you find you're not getting the help that you need, there's a forum for Paraview called Discourse. We'll put the link up in the video. Probably edit that in, but you can go there and just ask a question, and that's actively used by the Paraview developers and also heavy users of Paraview from national labs and other companies. So yeah, feel free to get on there and ask a question, and somebody should help you out with that.
Okay. And then, so then we got the Paraview GUI help, right? So you can always go up to Paraview and click help, and you saw that's where we got our example visualizations. But, there's also, you just click on the Paraview tutorial or Paraview guide, getting started with Paraview. Explore those help functions. They're really good. On the Mac, even if you can click on the search button for anything, or not the search button, but you can enter something in the search, and you'll be surprised at how awesome that is. Say I want to do a contour. I don't know how to do a contour. So you start typing contour, and Paraview will kind of guide you gently and forcefully there. let's see that, and then another key element for me is, I've used Paraview for a long time, but this question mark button, which is just terribly useful, right? I got, if you got some pipeline with 20 elements in it, and people have renamed them or stuff, you can always just click this question mark and it will tell you a ton of stuff about that particular filter or that particular source. And Paraview is really about chaining together sources and filters. So having this direct support and direct help for those is pretty useful. Let's see. So we're going to stop here, I think, and we're going to make sure that everybody can load the can, load the other examples. Look at selecting variables and kind of explore the things that we just did. Make sure that you can crush the can. Make sure you can repeatedly crush the can, make you feel good. Interact with stuff in 3D, change it to a 2D, interact with the 2D view, change it back to the 3D view, and then try this with the wavelet source and maybe explore some of the other sources or data sets that are available. And we will have a short break to do that, and then we will and everybody will be online and you can ask questions, and then we will come in with our second section, which is a little more involved. Follow along, create some Paraview pipelines and some pretty pictures. Okay, see you soon. So welcome to the Q&A. And during this time, I guess we will be monitoring the Discord, and we have 5 minutes, I believe, before we have to start the next video. And so everybody should be trying to get Paraview up, try to load some of these example data sets, and apply some of the filters that you just saw. And if you have any issues, ask. Hello, this is John Patchett. I apologize if I had an echo. Hopefully this maybe resolves it. You can keep us busy. Ask those questions. It's like we have 27 people watching. Might be 6 of us. On a Mac, not finding the data sets like the can one. I see the can.exe example, but not the data set. Okay. I wonder, I can try to share my screen here because we have how many minutes? We have 3 minutes, and I do have a Paraview up, I think. So let me share screen. So to open and find those data sets,
So for all of the operating systems, when you hit the file open dialog, there should be an examples in the upper left-hand corner of your open dialog. And that should have all of the 4 example data sets that I showed earlier. And I don't know if that's, oh, that doesn't look like it's showing up on YouTube. Let me see if I refresh YouTube here, if that, nope. I'll go ahead and stop sharing. Yeah, so if you do file open, in the open file dialog, you should see an examples in the upper left-hand corner of the open file dialog. And if you click on that or double click on that examples, that should get you the four examples that we were showing. And other than that, then we showed the, at least, and you're on the Mac. So let me find out where these things are on the Mac. Well, can one of our tutorial folks, thank you, Ken. They're probably deep in the applications folder. And David, I think if you're using Paraview 561, about the Paraview servers, that's something we can set up easily. Yeah, so if you're using Paraview 561, you should be able to just change out the Paraview -5.8.1.app with the Paraview 561. We will talk more about the servers a little bit, maybe during the next Q&A session. But I think we have to start the next video. But I can say more about the servers, and I'll prepare to say something about having a parallel distributed memory system running during the next Q&A. And at 9:05, I think we have to move forward. Hello, this is John Patchett, back for you. Hello, this is John Patchett, back for using filters. So our first step is we got Paraview fired up. And essentially, we're going to make this visualization that you see over here on the right. And so our first step is going to be to load disk out ref, and then highlight it in the properties panel, and then select the contour filter. So I'm going to come over to Paraview and do File, Open, Examples, Disk Out Ref. Double click it. Now, make sure it's highlighted. It's already highlighted. So, but I'm also going to click Apply in the properties. I'm just going to select all variables. Safe that way. And then I'm going to pick the contour filter. So we want to, in the contour filter, look back at our tutorial, we're going to contour by temperature and set the value to 400. So contour by is the properties panel thing. So you got to tell the contour what variable you want to contour by. And then I'm just going to double click in the value range, the isosurfaces value ranges. And I'm going to select 400. Notice in the
value range that there's some other options, like we could do multiple contours. We could add an entry and set that to something else explicitly. You could set a range of contours and go from, in this case, it goes from the min to the max and the linear ramp and picking 10 values, but we're not going to do that. And then it would just populate this this thing with a bunch of, or this list with a bunch of these values. Okay, but we want temp and 400. And so that immediately gives us this little mushroom cap. And let's see what else we were supposed to do. So we got, select contour, set value to 400, and you have to click apply, remember. And then let's color that by something else. So then we took a contour of temperature, but we will color it by pressure. So coming back to Paraview, to color it by something, right? We have contour highlighted here, got one render view, and we will just color it by pressure. There you go, and you can interact with it, zoom in on it. It's a very big mushroom cap looking thing. And okay, so I think that we are done with this step. Learn about the contour filter using the question mark. So remember that you can always, so we have this contour filter selected, and notice if I switch something in now that I have multiple things in my pipeline browser, as I switch between them, my properties panel updates. And I want to know more about the contour, so let me say, hey, contour. And then there's a lot of extra information here that you can read about the contour filter. Okay. So the next step will be to get this slide to advance, is then extract a surface. So we're going to try to make this visualization now that we see right here. So we're going to highlight the data set or the reader, right? So which is the disk out ref again, and apply the extract surface filter. And then color that by pressure and change the representation to wireframe. So highlight the original data set, right? I could click the eye and see where that is in contrast to the contour that we made. So I'm going to go to filters. This time I'm going to go to alphabetical and extract surface, which is right here. And I'm just going to click apply. And notice that gives us the full surface of the volume. We've seen that before, because even if we just did this, right, it kind of looks the same, but they're not actually the same. The disk out ref here, and we can see that with the information tab in the statistics, has 7,472 cells, but the surface only has 1,988. So we did reduce the amount of data we have here. And so what we want to do now is change this representation to wireframe. Oh, and click the eyeball on to say we want it. And then we're going to color that by pressure as well. And so there we go. Oh, and in the screenshot that we had earlier, or on the PDF, the background is black. So let's change that background color. So we got the palette right here, and I can just simply click on that and go black background. And then I want it to look nice maybe, and so I want my scalar bar, say over here. Maybe I want that scalar bar a little bit longer so I can understand it better, and so I can make it go much bigger and longer. And then maybe I don't want these axis coordinates anymore either, so I'll get rid of those guys. Okay, so going back to extract surface. Oh, and then I want you to save a screenshot here. So this is interesting. So you have this beautiful visualization that you've created. You want to put it on your report cover. You go, if only I could have a PNG. So you can come over here, and it's as simple as saying File, Save Screenshot. I will put this on my desktop, and I will call it delete me cylinder, and I will save it as a PNG, and it'll come up with the default image resolution that you have running on the screen right now, and I'll just say okay. And so now if I come up with a file browser here and I go to my desktop, I see delete me cylinder.png. So here's my screenshot. Another thing you might want to do, and I find myself in this situation frequently, is I want a certain aspect ratio or a certain resolution. And I want to make sure that I'm developing, my visualization with everything that I can in terms of the aspect ratio, so that when I save it in some given resolution, I'm actually going to get the correct output. And so if you go to View, we have this preview capability that says, hey, I'm going to do this in 1920 by 1080. And so now what I have is my render view. You can see that in this layout, in my render view, I have this 1920 by 1080. But also notice all my icons went away up here that allow me to do other stuff with that render view. But now this is more of a WYSIWYG. What you see is what you get. So if I want, I'm targeting a 1920 by 1080 visualization, I can simply do this. I can also add, so while we're here, I'm just going to add one more interesting thing, and that's going to be a text source. And so I go to the text source and I say, properties panel. And so instead of text, I'm going to say my discount ref, and apply that. And then notice with this filter, I could center it at the top, put it on the right, bottom left, bottom center. I can do these window positions. I can change the font size. And I could also, if I wanted put this somewhere else entirely, I can use the window location, and now, and then click lower left corner, sorry. And now I can move it and essentially put it wherever I want. Okay. All right, let's go back and see what the next thing is. So we saved a screenshot. We created an extract surface filter. Okay, so now we want to make this image. And this image comes from, looks interesting. Highlight extract surface filter, make it a surface representation, add a clip filter. And note is applied to the surface filter, right? And then check the show plane. So now we want to make the clip. So we want to kind of cut out half of the original cylinder, but show that surface still. So back to Paraview. On the extract surface filter, I make sure that's highlighted, and we'll just go ahead and make that a surface right now. And then with the surface, I'm going to do a clip filter. So clip filter is one of those convenience buttons up here, which is clip, and I could also get to it through file search. You go, oh, I know that I want the clip filter, and then I just double, or how you got to click on the button on top. And I'm going to get rid of the show plane. Suffice it to say, the plane here, what it's going to do is the filter is going to remove half of the data set on one side of this arrow along the plane that you can see here outlined with the red. And if I get rid of the show plane, it will just go away as soon as I click apply here. And so this is kind of interesting because if I show the plane again, it shows up. That's an interactive widget in the render view. And generally, if you want to do the clip, of course, you don't want to show all of this stuff that you use to actually do it. And it doesn't have to be axis aligned. You can drag this arrow and move this whole clip thing around. If you screw it up, you can always go back and hit the X normal, Y normal, Z normal stuff and move this around. You can move the bar up and down, or move the plane up and down. There's also an invert. So in this case, where this arrow is, the direction that it's pointing is going to get cut, and the other side is going to stay. If I got rid of this invert and did it again, it would actually change that direction. So I'm going to hit the invert again. It's default. And you got the apply, then get rid of the show plane. And there we go. Now we got that visualization. And so we're just basically showing the surface of the entire volume and then with the contour on it as well. You can see if I get rid of the contour, I just got that half surface. And let's see where we're at. Plane apply, use camera controls toolbar, turn visibility, clip off and on. So also in this part of the tutorial, I wanted to point out these guys again, in case you haven't experienced them. These are the axis aligned predetermined camera views. And so like if you go, hey, I know that I really like this front one, but then I want it tilted up a little bit and a little off to the left. And so you can get back to that position relatively easily. And you can also experiment with turning off and on the eyeballs for visibility. So the next thing I want to show is how to do a multi-view. So we're going to split the view horizontally and get two views in there. We will select the render view and the properties panel, add a clip filter. So we're going to make another clip over here and call it a solid clip. Rename the new clip filter to a solid. So I'll show you how to rename a filter in the pipeline. So if you get a lot of elements in the pipeline, it's convenient to be able to rename one. And then be able to make sure that you understand the difference between when you highlight one of these views. So the first thing to do is to get ourselves out of the preview mode. And I do that simply by checking that button, and notice that all my render view icons come back. So now I'm going to chop that guy in half. And so I clicked this button here, right? I could actually click it again and keep subdividing this screen space. But here I want to pick a render view. So I got this new view. I'm going to pick a render view. And if I click on this render view, notice that it's outlined in blue. And I could say, hey, I want to see the contour in there, right? And now I got this other render view to work with, and I'm just looking at the contour of the ball. Notice that it doesn't, that the color by and the representation is independent of this thing over here on the render view on the left. But our goal is to actually clip the plane now. Clip the original data set. So I'm going to highlight the original data set, and I am going to clip that. And it's not viewing right now. So if I go and then I move back to clip, we can see that it's turned on the visibility of these things. And I'll just click apply. And so now I have this solid volume that I've clipped, which you can kind of see this is empty like a boat hole or something. And this one is solid because I kept that internal geometry that I didn't have over here because we did the extract surface. So then I can make this thing look very similar to this one by going color by pressure, right? And so, and now there is this minor difference between the two, but sometimes, you know, that's an effect you want or you don't want. So then I could also turn on the contour in this space. Oh, but the contour in this render view, I set to point. So now I need to turn it back to be a surface. And let me color that by pressure as well so that it's all the same. And this one, notice the orientation axes are still there. So I'm just going to chop those guys out. Okay. And where are we at? Rename. Oh, we were going to rename the clip filter to solid clip. That's right. So let's come over here. So renaming the filter is pretty easy. So it was clip 2, right? And I can validate that. I'm going to highlight this render view, go over here, and I can make it go away, and I can make it come back. I'm also going to get rid of the show planes. So to rename this, I simply double click it, and forgot what I was going to rename it. And rename it solid clip. That makes sense. So it's still in this rename mode. So solid clip. And now when I'm looking at it, I don't have to like turn it off and on. I know exactly what that is. That's the solid clip. And okay. No blue highlight around the render view. We looked at that. We renamed the clip filter. We added a clip filter. Okay. And now we're going to link views. So a really convenient thing to do when you have two different views of the same data set, you want to link them together so that they kind of are oriented properly, especially if you're looking at substantially different things. So all you have to do is pick one of the views, and notice as I switch, remember they change. You have one that's selected at a time. And I can select one and just say link camera. And this little box comes up. And all you have to do is click on the other render view that you want to have it linked with, right? So now, if I interact with either view, the cameras are totally linked. And I can investigate more closely that difference between, say, having the clipping the volume versus clipping only the surface. You can see here, right, just the contour goes in. It disappears as soon as it goes inside that volume. Whereas here, you can see it go down and around. There's probably some other nuanced aspects here, like you can see the surface of that cut here, but here you can't see the surface of the cut. Okay. Like camera, interact with each view, experiment selecting render views and visibilities of the property panel. And here we're going to pause and make sure that everybody was able to do that exercise. This exercise, by the way, was in the Paraview tutorial for Paraview 5.6. And it was developed by Ken Moreland, and I nominally borrowed heavily from that to bring this to you today. I will see you soon.
So thank you, Ken Moreland, for working hard some years ago to create this tutorial that walked through a reasonably intelligent Paraview workflow. complete to do. So we are open here we have 3 minutes before the break, and you can ask questions. I guess while waiting for that, I'll make another comment on the parallel distributed memory client server aspect of Paraview. So essentially, using TCP sockets, you can fire up a parallel distributed memory Paraview server, and then you can have a client that can connect to that server via sockets. And so you have to be able to manage sockets, and oftentimes with supercomputers there's security issues, and a lot of people have dealt with the fact that back-end nodes versus the front-end node. Back-end nodes may not have access to the internet, so we can tunnel things for SSH tunnels to get back to a desktop client with a TCP SSH tunnel. And on the parallel distributed memory side, everything that you've seen here today so far can essentially happen in distributed memory parallel. The para, I always tell people, the para in Paraview stands for parallel. And every filter, nearly every filter, can be run in a distributed memory parallel way. Paraview uses MPI to handle inter-process communication, and it does it pretty seamlessly, actually. Like, you don't have to be some supercomputing parallel distributed memory genius to make this stuff work in environments that have already integrated it. If you have data on a remote server, it seems to just it works somewhat transparently, and a lot of those details are beyond what we were going to talk about here. And we pitched this as a 2-part class, so maybe IEEE VIS 2021, we might have a parallel component to that. So stay tuned. Are there any questions? Geodata. So whenever you have data that's not that's not easily accepted into Paraview, if you can figure out how to convert it, or get somebody else to write a reader in Paraview, or you can write your own reader. There's a large number of readers in Paraview, and so if you can figure out how to get the data in Paraview, once it's there, you can interact with it like any other set of data, right? Like, with the CAN example, if I wanted to put like the sphere source and make it look like a moon standing over the can or something, one could probably do that. That's a little more cinematic than most people use Paraview for. But there is a crew out of Germany that oftentimes makes Christmas cards, and they've used Paraview to make fantastic scenes of Santa riding his sleigh, and some beautiful scenes that are much more cinematic than strictly nerdly sciencey discrete properties of a can being crushed or something. It's somewhat flexible if you have the creativity. So I think that we have a half-hour break, which means I can get my coffee to be hot again, and I guess that we will be back here and the next part of this tutorial, which I think is Ethan Stam talking a lot about color and volume rendering, before we get to Ken really talking about color, and then some advanced rendering after the break. So during the break, I'm gonna walk away for 2 minutes, but I'll be back. And if you have questions, or you want to start using the chat system, feel free to, and we'll be looking at that, or at least I'll be looking at that over the break. So see you soon.
We present an algorithm for raycasting Hermite spline tubes, which result from letting a sphere trace Hermite splines that define its visual attributes. Since we do not employ tessellation, our method enables smooth curves and transitions of radius and color along the tube. Join us for an in-depth look at the intersection routine that enables raycasting hundreds of thousands of them efficiently in real time, and see what makes them a powerful new tool in the inventory of curve and line data visualization.
We have seen many visualizations for tree data structures, but when showing changes in trees over time, some focus on displaying hierarchy, while others highlight their changes. With split streams, we combine two approaches and their individual benefits. We evaluated our method in a user study and consider it a general-purpose method for the visualization of dynamic hierarchies. Our JavaScript library is openly available.
Analyzing urban heat island phenomena, which cause higher temperature in cities, requires to explore the relationships between climate and urban morphology. In an ongoing co-visualization framework, we propose different ways to visually explore both urban and climate data at a city block scale in order to support the analysis of urban heat islands.
Attention mechanisms have greatly improved the performance of many language models, yet with great power comes increased complexity. In this work, we present attention flows, a visualization that let users interpret the language model's decisions and gain insights into the underlying self-attention mechanism. We also support model comparison that helps to fill the gaps between models in different training stages.
CarxS is an authoring system which enables rapid creation of zooming-based scatter plot-like visualizations in just tens of lines of JSON. We contribute a declarative grammar for such visualizations, which captures a large design space. By working with multi-node database spatial indexes, CarxS enables interactive browsing of billions of data points. Come listen to our talk to learn more.
Ecosystems are complex and dynamic. To investigate the dynamic nature of ecosystems, we have developed a prototype of a visual analytics system based on empirical dynamic modeling, EDM. EDM is a set of analytical methods rooted in nonlinear state space reconstruction. Integrating EDM with dimensionality reduction, brush-linked visualizations, and visual summarization support understandings of ecosystem dynamics.
Position is believed to be the most precise encoding channel, but our perception and memory of it can still be biased. Past work has shown that the vertical position of bars in a bar chart is recalled in a biased manner, illustrating both an underestimation and overestimation bias of position. Here we find that the aspect ratios of the bar marks can cause this position bias, specifically resulting in overestimation for bars with wide ratios and underestimation for bars with tall ratios.
Digital humanities present great opportunities for testing new visualization approaches and evaluation techniques. However, and given the diffuse character and novelty of the field, it may also be intimidating for novel and senior researchers willing to get started in the discipline. In this paper, we propose a data-driven analysis of visualization for the digital humanities to identify key themes, authors, and relevant publications. So if you want to know more, please read our paper.
The classifier trained on the historical data may fail to classify the incoming data when the data distribution is changing. This phenomenon is called concept drift. To handle the concept drift, we developed the Drift VIS, a visual analytics system to help the expert understand when, where, and why the drift happens, and update the model to improve performance.
Smartwatches can track a wide variety of data. We are interested to learn which type of data people consume and how it is visualized. To find out, we conducted a survey with 237 participants. We found a predominant display of health fitness data, with data mostly displayed as icons with text. Based on our findings, we discuss opportunities for visualization research on smartwatches.
We present a flexible and easy-to-use software infrastructure for interactive rendering of large-scale display walls, either from on-site or from remote cluster. The display service can easily be configured to support a range of typical network and display hardware configurations. The client library provides a straightforward interface for easy integration into CPU and GPU renderers. We also demonstrate this framework for use in deploying low-cost alternatives for display walls.
How do you visualize the nanoscale, 1 billionth of a meter, for the public? As part of a Science Center exhibition, we developed an immersive environment that explains nanoconcepts by allowing users to explore nanoproperties. We reflect on how exploration, the confluence of explanatory and exploratory visualization, can be applied to visualization in public spaces.
We present the first generic design space and library for visual piling. Inspired by physically piling paper documents, visual piling describes an interface for spatial organization of visual artifacts into piles of partially overlapping items. Piling affords interactive grouping, arrangement, previewing, browsing, and aggregation to reduce the complexity and support comparison of large collections of small multiples.
Morse complexes have shown a great utility in understanding the topology of complex scientific datasets. The noise in the scalar field, however, can significantly distort the Morse complex topology. Hence, we study the extraction of Morse complexes for ensembles of noisy scalar fields through their uncertainty visualization using our proposed statistical summary maps.
When visualizing data in a realistic rendered 3D environment, it is important to represent the data in a readable way. In our work, we investigate how the opacity affects the readability of a 2D shape and determine useful opacity ranges. Therefore, we performed a user study with different overlay configuration like filled, striped, and dotted pattern, their density, and considered the effect of an outline.
In our paper, we address the problem of navigating complex multiscale and dense environments, such as these molecular models. We present a technique for browsing a model by clicking on textual labels, which we call hyperlabels. This allows the user to intuitively navigate the hierarchical organization of the model. For more details, read our paper or watch the talk.
Pixel Clipper allows visitors to quickly and expressively extract visual clippings from visualizations and add comments to them. The clippings are useful for engaging the public with complex datasets because they are entry points into the visualization. This can be applied in a wide range of engagement experiences, such as the use of facilitated and ambient displays at public engagement events.
We propose an interactive ensemble analysis framework that provides flexible interactive exploration of the ensemble data. Time series characteristics of data can be obtained by fast browsing time steps. The region stability heatmap view shows the stability of the selected region and provides region adjustment by directly clicking.
Text alignment is a fundamental technique in many text-related domains. In this survey, we cover 3 text alignment scenarios: collation task, text reuse detection, and translation alignment. On the basis of those scenarios, we reviewed the existing text alignment visualization approaches and discussed their advantages and drawbacks. We finally derived design implications and shed light on related future challenges.
Deep learning models have become ubiquitous, but we often lack interpretations for their decisions. We developed a visual analytics system to interpret models that perform multi-class DGA classification. For each layer of the model, we visualize clusters inside its activation data, showing how classes and clusters relate to each other. In addition, we provide a decision tree to explain how these clusters are constructed.
In this presentation, we introduce a Provenance library, Track, which makes implementing Provenance in web-based tools easy. Track introduces a novel storage model for web-based provenance tracking and has an associated history visualization, which can be fully customized. Track also contains multiple ways to save and share individual states or entire sessions of an application, and ensures that exported data is easy to analyze in interesting and unique ways.
When developing a deep learning model, people typically struggle to optimize hyperparameters that affecting the model performance. To relieve the pain of this manual trial process, AutoML has been developed as a solution. However, to maximize the potential of the AutoML, people should identify a good AutoML setting for their task. Hypertender helps to maximize the potential by visualizing AutoML algorithm behavior and guiding effective hyperparameters.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
Do these three essays construct their argumentation similarly? Where in this table of argumentation data from the previously seen texts can I find certain argumentation patterns? Do these three argument maps depict the same argument? We have developed a visual analysis system for argumentation in essays that can answer these questions at a glance. You want to know how it works? Come to my talk.
We present StratGraphics, an approach for designing data-agnostic and fully reusable visualization templates. StratGraphics follows the inverse workflow that common data-driven systems. Rather than starting from data, designers construct visualization structures without relying on a data schema. Data tables are shaped later from the structure of graphics. We demonstrate the power of the approach through a gallery of visualization examples.
Progressive visual analytics provides intermediate results in the middle of computation to address a long computational delay. However, such intermediate results are uncertain, so findings from these results can turn out to be incorrect for the entire data. In progressive visual analytics with safeguards, we suggest to risk the uncertainty, but we allow humans to leave safeguards every time they risk the uncertainty.
The visual analysis of large-scale data from complex systems such as electronic health records has become increasingly prevalent, but can be prone to a variety of selection bias effects. We introduced dynamic reweighting, a novel approach to selection bias mitigation that helps users craft bias-corrected visualizations. This approach is implemented in the Cadence Visual Analytics tool, which provides visualizations of and control over the dynamic reweighting process.
Evaluating alternative interpretations is an essential part of complex sense-making, but the resulting ambiguity is rarely considered in the design of visual analytics systems. Avalanche forecasters rely on sparse and human-produced data to assess avalanche hazards, often resulting in ambiguous interpretations. We used simple glyphs and unit visualizations to specifically consider and support ambiguity in the avalanche forecaster's sense-making processes.
A testing environment for continuous color maps. Many other fields in the computer science do it, we should do it too. With our work, we introduce the approach of using test functions as a standard evaluation method. We present a test suite for continuous color maps implemented in the CCC tool. Adapt the task to your requirements at the interactive testing section and observe them at the testing evaluation section.
Entities and their changing relationships can be modeled more precisely as temporal hypergraphs, but hypergraph models are difficult to explore and refine. By leveraging domain-specific geometric deep learning models and a new multi-level hypergraph visualization, our technique allows for the direct integration of domain knowledge into the machine learning process. The multivariate hypergraph model structure can be analyzed on different abstraction levels. Simultaneously, experts can integrate their domain knowledge on the fly, and then explore the refined machine learning model.
We present Lyra 2, a system for designing interactive visualizations by demonstration. To design interactions in Lyra 2, users directly manipulate the visualization canvas. The system interprets demonstrations using heuristics and suggests possible interaction designs. We find that Lyra 2 enables rapid prototyping of an expressive range of interaction designs. We're excited to share this work with you.
Linking and brushing is very useful for interactive visual data exploration. Data-driven brushing tools are getting popular recently and achieve good results, for example the Mahanoda-based brush and the CN-based brush. However, these brushing tools are optimized by the data from a large number of users, which are not suitable for everyone. In this paper, we introduce an adaptive brush model which takes the user in a loop to improve the brushing accuracy.
String graphs are variants of stack graphs with curve-based line, and the main factor affecting its readability is the sign Lorentz through a perceptual inconsistency of the orthogonal and vertical direction. Aiming at reducing its impacts, we revisited the baseline formulation and proposed the concept of composition to help the string graph layout optimization. The result shows that our algorithms perform better than the others.
Nowadays, online services are used for all kinds of activities. Strategies to increase the situational awareness of personal data stored by online services are needed. We present Transparency VIS, a visual, interactive web application. It allows common internet users to explore their personal data exports, which can be requested from online services like Facebook, Google, Instagram, or Twitter. Feel free to try it out online.
Hands-on cybersecurity training represents a domain where visual analytics can significantly improve the impact of teaching process. We describe this new application domain and introduce a conceptual model that can serve as a framework for the development of analytical visualizations. Unified training lifecycle will be discussed from the perspective of different user roles.
We propose X-matrix, a novel method for random forest interpretability. From a random forest model, a logic rule is extracted from each decision path on every decision tree. Once the complete set of logic rules is obtained, visual representations can be built for global and local explanations. X-matrix, making random forests interpretable.
Billions of biologging records reflect animal behaviors on many temporal spatial scales, yet segmenting the time series on multiple scales is often avoided or impeded. Hence we present our Multiseg VA platform with its 3 contributions. First, Multiseg VA contributes tailored visual interactive features for multi-scale segmentation. Second, we show a new visual query language to flexibly configure scale-wise techniques and parameters. This VQL consumes a domain-oriented set of techniques, our third contribution.
Transitions are widely used in data videos to build seamless changes between video narrative. As the attention cue, they can not only keep viewers oriented but also express narrative information. After conducting a content analysis on the transitions in the dataset, we provide a comprehensive taxonomy of narrative transitions in data videos.
Deep neural networks are vulnerable to maliciously generated adversarial examples. This brings high risk in applying these networks to safety-critical applications. We developed a visual analytics approach to explain the root cause of such wrong predictions. Our contribution contains a constrained data path extraction method, a river-based visualization, and a contribution analysis method.
A dynamic graph models changing relationships between entities over time. In this work, we present multi-scale snapshots, a visual analytics approach to provide an overview of a dynamic graph at multiple temporal scales. The approach consists of 3 steps: creating multi-scale temporal summaries, applying graph embeddings, and the semi-automatic visual analysis. The combination of these steps lets us visually explore how temporal and structural properties affect the overall dynamic graph.
Our research goal was to design an efficient preview method of the parallel vectors operator through direct volume raycasting. As such, we present the first implicit raycaster of parallel vectors feature curves that reaches real-time performance for interactive parameter exploration and preview by applying tensor product calling and a sectional Newton descent.
Confusion flow is an interactive visualization for the performance analysis of classification models. It introduces a novel temporal adaptation of the confusion matrix, which lets model developers compare the learning behavior of multiple classifiers over time. Find out more about confusion flow in our talk or in our TVCG paper.
If machine learning were like education, we would like to test what concepts our student, the model, has learned. Has it learned the concept of object rotation? Does additional text help with object recognition? We need a methodology and platform for conducting such tests. In this paper, we present a novel visual analytics tool that enables hypothesis-based evaluation of machine learned models.
Ray tracing techniques can create images of astonishing realism and beauty. In the last years, the performance of those techniques has been increased significantly using dedicated hardware. Who thought that it's also possible to accelerate this? We show how to dramatically accelerate force-directed graph drawing with RT cores, yielding a speed up of 4 to 13x. If you want to know more, please see our talk.
A Morse-mean complex is a topological descriptor that captures the gradient flow of a scalar function. The best-known approaches for its computation incur large runtimes for bigger datasets. We address this gap by introducing the first completely GPU parallel pipeline, which achieves speedups of up to 7x, with our individual algorithms attaining speedups of up to 129x and 4.5x.
Druid JS is a JavaScript library for dimensionality reduction where we implemented 11 DR methods. A typical use case for Druid JS is a web tool using DR. You just need to import Druid JS, create a DR object, and then call the transfer method. That's it. See the talk, the paper, or the supplemental material for more information.
Data videos are quite popular nowadays. They usually show changes in the data. However, creating a data video requires multiple skills, and the process is usually laborious and iterative. Our approach focuses on automatic and interactive visual enhancement of important changes in time series data with data video.
This is a picture of a Tableau visualization within the browser. The data behind the visualization does not exist here, and Tableau is not running. This is just an image. However, parts of this image are fully interactive. Please join our presentation to see how we can share interactive visualizations across the web, free from any dependency on data or visualization application.
In our current work, we visually compare two cohorts of segmented and classified tissue images, originated from single-cell omics data. To that end, we developed data-driven and interactive workflow, implemented in a multi-linked view.
Okay. Welcome back, everyone, to the post-break Paraview tutorial at IEEE VIS 2020. We're excited to be here, and we're excited to present the next pre-recorded video session, which is Ethan Stam with volume rendering and a couple more filters and some color map editing. So let's take it away.
Hello, I'm Ethan Stam, and I'm going to be talking about two more filters and briefly going over the color map editor in Paraview. So the two filters I'll be talking about are the stream tracer filter and the glyph filter, and also going over color maps and volume rendering and using the color map editor to show some interesting stuff. So the first thing we're going to be doing is creating some streamlines with the stream tracer. So the steps we're going to follow to do this is, of course, going to be resetting your session so you have a nice fresh Paraview. We're going to be using the disk out ref dataset again, applying all variables or turning on all variables. And we're going to be using the stream tracer filter, which is one of these common filters shown in the toolbar. So let's go ahead and do that in the GUI. So step one is reset session. Yes, I'm sure. And we're going to file open, examples, disk out ref, turn on all variables, apply. So now we have the disk out ref, and we want to apply streamlines. So the stream tracer filter is the 1, 2, 3, 4, 5, 6, 7, 8th icon in the common filter toolbar. So we're going to click that, and in the properties panel, we want to change, I have my advanced turned on. I'm going to hide the advanced properties, make it a little easier to go through. And we want to change the seed type from high resolution line source to point source. And go ahead and click apply. Okay, great. We have these nice streamlines, but if you see, we have this weird sphere at the bottom, which is where these streamlines originate from. So I want to hide this sphere, and to do that, you go back in properties and you can uncheck show sphere, and it goes away without clicking apply. So I'll go ahead and reset my camera, and you should have something close to what is shown in the slides. So one thing to note here is, even though we have these streamlines, they're all 1 pixel width, and it's kind of hard to tell which lines are in front of the camera view and which lines are in the back. So how do we do that? How do we have a better representation to show where these lines are and have a better depth perception? So we can create fancy streamlines with a tube filter, and the steps for that is selecting Stream Tracer 1 in the pipeline browser and adding the tube filter, and that's it. So let's go ahead and do that in the Paraview GUI. So we have Stream Tracer 1 selected, and we are going to do the tube filter, which is not one of the common filters. So at the top we'll go filters, alphabetical. In a Mac you have to scroll all the way down. It doesn't pop up in those nice 3 columns like it does for Linux. Go all the way to the bottom, and we'll select the tube. And we're going to take the default properties for the tube filter. So apply that. And now you can see we have these nice tubes with some shading, and it really helps to show which lines are actually in the front and gives you a little better idea of the depth of these streamlines. But it sure would be nice to know which direction these streamlines are flowing. And an easy way to do that is to use the glyph filter. So we're going to add some glyphs that represent the vector velocity to show which direction those streamlines are flowing in. So the steps for that, we're going to reselect Stream Tracer 1 in the pipeline browser. We're going to add the glyph filter, which is another one of the common filters in that toolbar, and we're going to set these few properties in its properties panel. So let's go ahead and do that in the GUI. So we're going to go back and select Stream Tracer 1. Pick the glyph filter, which conveniently is 1 to the left of the stream tracer. And in the properties for the glyph filter, I'll make this a little bigger. We want to select cone for the glyph type. The orientation array, we want to select V. And the scale array, we're going to also select V. So let's go ahead and apply that. Okay, so now you can see we have these giant cones. We can't even see where the streamlines are anymore. But yeah, this is not looking right. So a way to adjust the size of the cones, you go to the scale part of the properties panel, and you can drag this slider down to lower the scale of these cones. You see that's a little more reasonable. Or alternatively, there's these 2 buttons, so we can do half, so now we're at 0.06. We can do double. We can do double again, so now they're a lot bigger. Or we can click this reset, which will give us a reasonable size. So go ahead and click the last one, which is reset using current data values, and apply that. So great. Now we have these streamlines that show not only the direction of the flow, but based on the size of we have these streamlines that show the direction of the flow with the glyph filter, but also show where the velocity is the velocity magnitude is the largest based on the size of these cones. So let's go ahead and color the glyph filter. So we have the glyph 1 selected in the pipeline browser, and let's color that by velocity. Okay, and you can see our color bar as of now goes from 0 to 22, but you can see based on what is being shown in our render view, obviously nothing is coming close to 22, so what we want to do is rescale to visible data range. And you can see we're actually closer to 0 to 13. So now that what is shown in our render view actually corresponds to the color bar. Okay. So that's the stream tracer filter and the glyph filter. Okay, so next we're going to look at the color map editor. So there's a lot in the color map editor. I'll show you a couple of things that are very useful, particularly when looking at volume representation of data. And I would strongly encourage you to just go through the color map editor and explore a lot of these things on your own and see what works for you, what doesn't work for you. And yeah, just try some of this stuff out. As John said, it's hard to break. So let's go over to the Paraview GUI and work on the color map editor. So we're going to reset session. Yes, I'm sure. And we're going to file open examples, and this time we're going to use head.sq.vti. Make sure scalars are turned on and apply. And we are going to color by the variable scalars and show the representation as the volume. Yes, I'm sure. So we'll show the volume. Okay, we have the head. So now we're going to open the color map editor, which is this little button on the left as we showed before. And that pops up. I'm going to close this guy a little bit so you can see the head a little better. And the first thing that pops up in the color map editor, well, the first thing that catches my eye is this big linear ramp. So this is showing the opacity of the color bar. So as it gets more towards these lower values, the blue side of the color bar, the opacity goes down to 0. As it goes up to the higher values, or the red side of the color bar, the opacity is up to 100%. So you can grab these little points and drag them up, and as you can see, the more I drag it up, the more opaque this side of the color bar is becoming. You can also create a control point by clicking anywhere in this graph, and then you can drag that around and play with that. Down here, you can play with the data range. So we're going from 0 to 495. We can lower it, or we can shrink that. So let's say we go from 1600 to 495. But I don't really want to do that. So one thing that's handy is we have redo undo. So I want to undo that. And as you can see, we are, well, let's go back all the way to 0. Oh gosh. Okay. I just want to go to 0. Are we back? There we go. There are a bunch of undos, and now we're back at 0. Okay. So we have the head. Let's say, for example, I'm particularly interested in the skull. So you can use this to hide and show particular parts of this representation. So let's see how to do that. So now that I've created this third control point in the middle, the first thing I would do, it takes a little bit of precision to click the exact point you want, but you can click delete when you have one of those highlighted to remove it. Try and click that guy. Okay, I got it that time. I'll drag this all the way down to the bottom, the middle one, so that means everything on the left side of that control point is now hidden, and you can see some of the stuff on the right side. So now I'm going to scrub this guy along the bottom to try and find out where it becomes just the skull, or where everything but the skull is hidden. So I'm going to drag this a little further left until, okay, so right around 1000, more than the skull starts popping up. So we want to go back, and that looks good. That looks good enough to me. So this is just the skull, but as you can see, there's parts that are still fairly see-through, and I don't particularly want that. And those parts that are see-through correspond to this lower end of the ramp, where the data values are more translucent and more you can see through them. So I'll add another control point and try and increase those a little bit. You can get all the way to where it's almost a straight line. And yeah, I like that a lot better. Also, see how high we can get. Let's stick with this here. I like the way that looks. So now we just have the skull. I'm going to rotate that a little bit. Okay, great. I like that. So now I kind of want to get some context on where the skull is inside the rest of the head. And the rest of the head is this part on the left that's now hidden. So I'm going to add 2 control points again. I'm going to drag this one all the way to the bottom, and I want to scrub for the part where it starts to just be the skin and not anything else on the outside. So as you can see over here, there's some blue on the outside, and I'm going to scrub to the right, scrub to the right. Keep scrubbing. Okay, that looks reasonable. So it looks like I just have, I have his ears, his neck, some kind of weird stuff popping up, but I'm okay with that for now. Like over here, you can see that. I had 2 more control points because I want to have this distinction between, where his skin or where the skin is and the skull. So this, everything in between the skin and the skull is hidden, and then everything outside of the skin is hidden. So I'm happy with that. Let's go on with that. I'm not too happy with this red to blue color map, however, and you can change that in Paraview. And the way you do that is also in the color map editor on the right side of this ramp. Here's this little folder with a heart on it, and it's called choose preset. So we'll click that, and some options of color bars will pop up. So these are the default. There's a lot more. If you select all in this combo box on the top, and I would highly recommend just going through these and playing around. Ken will give you a lot more later on color theory and when to choose color bars in particular data sets. So stay tuned for that. But let's go ahead and select one of these guys. Just for fun, let's select X-ray. So you highlight it and click apply. Oh, sorry, click import. Click apply and close. So now you see we have this color bar applied now. It's a grayscale white to black. One thing I want is I'd rather have the skull as the white part and everything else is not, because bones are white, so it makes sense to color them white. One thing you can do is invert the transfer function or flip the color bar around, and that's one button above the choose preset button. So let's go ahead and click that. And now you can see that the teeth are whitish. The skull is, it's kind of white. It's a little more gray than white, but I'm happy with that. And I'm not too happy with the way the background looks though. So there's a couple ways you can change the background color. I normally go into the properties panel and toggle advanced properties. And then all the way at the bottom is the background, and you can change this to gradient image skybox. We're going to stick on single color, and let's go ahead and choose black. Okay, I don't like this grayscale color bar anymore with this black background, so I'm going to go back in and choose a different one. This time let's try the linear green. I'll apply that and close, and okay, I like that well enough. So yeah, I'm happy with that. And just to reiterate, if you want to hide the axis down here on the bottom left, up here you click this guy, unshow the orientation axis, and yeah, that's a really brief overview of the color map editor and some really nice things you can do with that to highlight certain areas of your data set. So that's it.
Okay. I need to. Okay. Yep. YouTube is muted. So sorry about that, you guys. I was rapidly trying to respond to YouTube A comments by actually trying to do that. My intuition is that you can have multiple volumetric data sets simultaneously. And perhaps somebody will respond to that while I'm talking here. And in the color map editor, to refer to that head SQ. I think what you're looking for is you have to color by a variable. And so when you say to do a volumetric representation, you have to pick a variable to color by, just like you would if you were doing a surface rendering. And so we do have a couple of minutes. I think that we probably have we have 7 minutes left before we start the next video. So if there are more questions, or if we are not getting the answers incorrectly, you can feel free to fling questions at us. And so you can mix transparency too. Another way, somebody had asked earlier about transparency. And so something that we do frequently is have multiple geometric sources, some of which have varying degrees of opacity that allow you to, in some cases, create this feeling of volume rendering. And then I certainly, we've had surface rendering mixed with volume rendering, so that's a possibility. And there's there is a visual overlap, it might not mix correctly. Yeah, and I think if you had multiple volume renderings in one space and the colors weren't mixing properly, that might be considered a bug and worth noting. So we do have about 5 minutes. And then we will hear a lot more about color. The blank color map editor to refer to the head SQ. So going back, I do think, so on the NCAR question about how did the color map editor get set to refer to head SQ, mine is blank. I think if you select in the pipeline browser the head SQ data set and then select volume, and then you have to select what to color by, and then if you edit the color map, you should get the correct scalar field being volume rendered. And what about creating surfaces from volumetric data? And so, my array name. Okay, so surfaces from volumetric data, you can create contours, you can create cut planes, you can extract the surface, or you can just render the surface in the representation. And I'm not sure about the my array name equals or to none. So Carl, when you're doing that, are you loading the head data set, and then you select the head data set in the pipeline browser, and then when you set the representation, you should see all the available scalar fields. Yes, one of the problems with doing this online is we can't see your screen. So let me, would it be possible to render two variables? Yeah, so one of the things you can do, you can do things like contour by one variable and then color by another variable. You could also have two sources. So you could like, something that happens in Los Alamos frequently is you can mirror the source. And so you can have on one side, you have it colored by one scalar field and the other side by another scalar field. We've certainly done other visualizations where we have some volume renderings where we have something colored by pressure and everything's adjusted to have the pressure colored properly or highlighted in the color map editor, and then also have something else that highlights the temperature, and then we've overlapped those things together, which may or may not be good visualization techniques, but I believe you should be able to do that. And I think the key, if you want like the identical surfaces or something colored by two different things, the way to do that is to, you could load the data set twice, or you could copy the data set, like use the calculator filter or something to get another element in the pipeline, because you can only color by one. For every element in the pipeline, you can only color it by one color map. And so if you get the same data set essentially twice in the pipeline, you can color it by two different color maps. Okay, so we are going to switch over to the next color video, and I will continue looking at the questions and trying to answer them as Ken Moreland's video takes over.
Hi, my name is Kenneth Moreland from Sandia National Laboratories, and today I'm going to be talking about the effective use of color within the Paraview application. So color is one of the most important elements of visualization. Most visualizations we do in Paraview use color to represent numbers in some way, as we've seen in many of the exercises today in this tutorial. So thus, using color effectively is very important when communicating and understanding data. To demonstrate this and to motivate this talk, consider these two visualizations. Now these are the same data with the same visualization parameters except using different colors. On the left is a color map that is very common, but is also known to be very poor. However, if you look on the right, with the better colors, you can clearly see that there's a shock wave moving through the material of the simulated apple. On the left, this important feature is there, but it's invisible due to the poor color choices. So as you can see, good color choice is very important. If you do not choose good colors, you may miss out on the physical phenomenon that are important to you. Now, color itself is a fascinating topic, and there are lots of things to talk about. In fact, there's another tutorial at VIS this year that's talking just about color. Now, I'm not going to go into that much detail, but I'll briefly cover the basics of color so that you'll be able to use it effectively in your visualizations. Now, it will come as no surprise to anyone with eyelids that we see when light enters our eyes. The light enters the pupil, gets focused by a lens, and is projected on the retina at the back of the eye. Now, the retina is covered with cells that react to light. Light itself is just a special type of electromagnetic radiation. Electromagnetic radiation covers a broad spectrum of phenomena that includes radio waves, microwaves, and X-rays. What distinguishes the different types of electromagnetic radiation is its wavelength property, which is the physical distance between the peaks of its wave pattern. As you can see, light, which by definition is the electromagnetic radiation of wavelengths that the eye can sense, is actually a pretty small part of the full electromagnetic spectrum. As we look at the different wavelengths in the visible light part of the spectrum, we see that each wavelength gets interpreted as a different color, and these, by no coincidence, are the colors of the rainbow. So this provides us with a big clue on where colors come from. It's our interpretation of the wavelength of light. But it doesn't tell us everything. In particular, you will notice that not all colors are represented by a wavelength. For example, colors like brown and pink are missing. The reason is that in the real world, you rarely experience light of a single wavelength. Rather, you experience a mix of light. And the combination of light with different wavelengths can be interpreted as even more types of colors. So this raises a question of how we can describe and reproduce colors. Do we have to capture every wavelength of light to reproduce a color? Fortunately, as it turns out, the answer is no. So there are different types of light sensors in your eyes. The sensors that help distinguish colors are called cones due to their shape. A person with usual vision has 3 types of cones, and each type of cone will produce an activation response that varies based on the wavelength of light, as you can see here. So, physiologically speaking, the brain interprets colors using only the activation levels of these 3 signals. This gives us a corollary. We know that color is perceived through the response of these 3 cone receptor types. Therefore, any color can be represented by the intensity of 3 given wavelengths based on their relative responses. This is known as trichromatic theory. This is what makes color video possible. So as you look at this video through your monitor is actually emitting little dots of red, green, and blue light that are being mixed together to form most of the colors that your eye can see. So why do we use red, green, and blue? Well, it's because they're the 3 most separated colors in the visible spectrum, and thus do the best at reproduction. Since your monitor reproduces images by mixing red, green, and blue light, it is only natural to define colors using intensity of red, green, and blue light used. This leads to the standard RGB definition of colors that you probably all have used at some point when selecting colors with programs on your computer. You can think of the red, green, and blue intensities as dimensions in some abstract space. We can draw that space in 3D, and you end up with a color cube like the one here. Now, so far, I've really only talked about the physical properties of colors. The inclination is to treat each RGB color as an equally unique color. This is not true. In fact, as we look at different types of colors with different intensities of light, we interpret them differently and can tell the difference in different amounts. So there are lots of fascinating aspects of color perception that I'm not going to be able to go into. The one impression you should leave with is that the relationship between the RGB values and how you actually perceive the colors is very nonlinear. To demonstrate that, I like these results from an informal survey done by Randall Munroe. Munroe, who is best known for his XKCD internet comic, asked thousands of visitors to his site to provide a name to a random color that he provided. After processing the data, Munroe divides the color cube into regions with the same common name, some of which are summarized here. As you can see, there's a surprising amount of variability in the size of these regions, even for common colors. The green region is huge, the yellow region is comparatively tiny. There's lots of color diversity between red and green, so between red and green we have the entirety of orange and yellow, but there's comparatively little between green and blue, just various different names for bluish green, or greenish blue, or light blue. It's this variability that can cause trouble if you naively transition between colors. And this is where the visualization at the beginning went wrong. The image on the left uses colors that are simple transitions in RGB space, but big changes in green hues are less noticeable, and this is where our shockwave got caught. So if we look in the center of these 2 color maps, we see that the rainbow hues have a large region of green colors that look pretty much the same, whereas the perceptual colors do not. Studies on the human visual system have generated special color space that more closely model colors as they are perceived. And the plot on the right shows what's known as the LAB color space. The axes are labeled as L for luminance and then 2 generic A and B dimensions for the hues. It is designed in such a way that if a color in this space is equidistant from 2 other colors, then the difference between the pairs of colors will seem the same when we view them. As you can see, the shape of the color cube is warped in this space in a very nonlinear way. Since color maps in Paraview are defined by interpolating space between sparse control points, it is usually desirable to interpolate in this lab space to get proportional transitions. If you look at the color map editor in Paraview, you will see that there is an option to interpolate in LAB space. You usually want to select this option if you need to edit your own colors. You still select the colors using the standard RGB or HSV values in the color browser, but the interpolation between them changes. The trick, of course, is selecting the control points so that they are evenly distributed. Now that we've discussed the perception of color, let's talk about what makes for a good color map. Here are some general elements of good color maps. We've already talked at length about what it means to be perceptually uniform and why it's important, so I won't dwell on that one again. In general, you want to maximize the amount of discrimination. That is, make the colors change as much as possible so you can see more changes in your data. You want your colors to have a natural ordering. A viewer should be able to tell which colors are low and which are high without being told. For example, dark versus light, saturated versus unsaturated, or cool versus warm. Sure, you have a map widget to look it up, but studies show that if your colors have a natural order, and by natural I mean perceptually natural, they can be translated faster into numbers in your head. Furthermore, naturally ordered maps are better for several tasks, such as estimating the average value that you're seeing across an entire model. Paraview is most commonly used to visualize things in 3D, so it's also important to pick colors that work well on 3D objects. Keep in mind that dark colors hide the shading cues necessary to determine the shape of the object. It's always a good idea to make sure your color map is as friendly to colorblind people as possible. The term colorblind does not mean you cannot see colors. It means that there are deficiencies in the activation for one or more types of cones, and so fewer colors can be resolved. So if we look at the image on the right, we see a simulation of how a colorblind person might see the image at the left. For this type of color blindness, which is a common color blindness between the red and green colors, it's not possible to differentiate between these two colors. Finally, the most self-evident and most difficult to define quality is the attractiveness of the colors. This, of course, is a very subjective metric, but we should avoid color combinations that are just plain ugly. Now, this may not seem like an important consideration, but in fact, you'd be surprised at how more likely someone is to view and analyze your visualization if they find it attractive. What makes color map design so difficult is that these elements tend to be mutually exclusive. For example, let's say you wanted to add more discrimination to your color map to see finer features. You could do this by adding more hues. However, this tends to reduce the implicit ordering since hues don't order well. There's no necessary order perceptually between, say, red and yellow. It also means that colorblind people who discern fewer hues might not be able to read the map. Instead of hue, you could try to increase discrimination by adding luminance variation. Unfortunately, to have a lot of luminance variation, you are going to have to make regions of dark colors, and this is going to make it harder to see 3D shading. Although I don't show it here, moving the luminance up and down a lot can also hurt the implicit order, because dark to light colors are one of the biggest cues to the order of the colors. The upshot is that there's no perfect color map. And furthermore, designing color maps is hard. Thus, to make the color selection easier, the color map editor provides a favorites button that comes loaded with lots of pre-made color maps. I don't have time to go over all of these, but I will cherry pick a few. The default color map is this smooth to warm, cool to warm color map. It's not particularly bad at anything, but it's designed to be particularly 3D friendly and have good implicit ordering. It does sacrifice some uniformity for smoothness, and it sacrifices some discrimination to be 3D friendly. If you want to add more discrimination, there is an extended version of the cool to warm that makes the ends darker. It also sacrifices some smoothness in the middle for more color uniformity. However, the dark ends may make it less appropriate for some 3D models. Now at VIS, we like to bash the rainbow color map. This is the color map I showed at the beginning of the talk with the apples as a bad example. It is for this reason that lots of practitioners at VIS discourage its use. The naive rainbow map color is in Paraview, but it's hidden because we prefer you not to use it. Now, to be fair, the rainbow color map does have some good points to it. It has quite a high discrimination, except in that wide green area we talked about. It's also quite 3D shading friendly, and many people find the colors very attractive. However, as discussed, its interpolation tends to lead to color distance perception problems. The order, while physically meaningful, as in the wavelength of light, really has no meaning to the visual system. And it is problematic for colorblind people, as I showed earlier. Because we know people can use the rainbow color map no matter what, Paraview provides a corrected version of the rainbow colors. The interpolation is now more uniform, so note the length of each hue has changed quite a bit. However, there's no fixing the issues with the implicit order or the colorblind use. Paraview also contains some community-defined color maps. These tend to be very good on many aspects, but tend to be dark at the low end, which might be problematic for 3D models. Finally, if none of these color maps seem to suit you, you can try looking at the full list of color map presets available. Some of these color maps are better than others, so mileage may vary. If all else fails, you can use the color map editor. This is the easiest if you have specific values with meaning, and you can assign logical colors to these values. So in conclusion, remember that the perception of colors can differ greatly from the physical generation of colors. Be careful of self-evaluations, where you look at that and you say, well, I think this is good and I'm performing very well at it. Perceptual studies show that subjects tend to subjectively evaluate bad color maps more highly than they objectively perform with them. Your best bet is to interpolate in LAB space and also to assign colors that are meaningful for different values of scalar values. Remember the perceptual elements of style. We want uniformity, discrimination, order, shading, be colorblind friendly, and make it attractive. We suggest using a predefined color maps where possible. That's most certainly what I do almost all the time because frankly, it's just easier. As I stated, good color design is very difficult, and it's easiest just to pick something that is already readily made. And with that, I thank you for listening, and I believe we'll be able to open up for questions. Okay.
So we have 5 minutes.
5 minutes, yes. Does anyone have any questions about, the color? Color theory, color application, anything we're talking about. It's a little bit of an offshoot from the rest of the tutorial, but in years past we found colors is actually a really important important part of visualization, and it's important to understand the basics of their application when using a tool like Paraview or really any other visualization package.
Yeah, as a color challenged person, Ken, I can say that even a little bit of this color theory seems to go a long way, especially when I have to make a picture that looks good. Oftentimes in my career, I've spent, I've said, oh, look, I can make a picture. I've technically got it correct. And so somebody with good color and art skills can make a good picture in Paraview, but actually being able to do that yourself is a good.
Okay. Looks like we got a question about implicit order, and I did sort of skip over implicit order a bit. What I mean by implicit order is, perceptually how you think about, what you consider the order of colors. So there's been some perceptual studies where participants will be given some set of colors, perhaps, those paint chips that you see when you go and select paint. They have those, paint samples. So they'll give participants different samples of that, or they may do it digitally where they'll show different colors on the screen and ask participants to order them from, low to high. And there's some colors, choices that people just naturally pick the same order no matter what. For example, if you just give grayscale colors, black, various shades of gray to white, almost uniformly, everyone will pick the darkest color to varying degrees to lighter and lighter to finally the lightest, or vice versa. Sometimes you'll get it flipped, but there'll be a standard order that you get for those colors, and luminance tends to be a particularly good one for enforcing sort of this natural order. Saturation tends to as well, where for example, you have some saturated hue like blue, say. So you got a dark blue going to various shades of lighter blue, perhaps to completely unsaturated white or gray. People tend to order those consistently as well. You don't have to tell them how to order it. They'll just naturally, if you say, hey, order these from low to high, they'll just do that. If you go to colors like from the rainbow, you just give people, these various colors. You give them red and orange and yellow and blue and green, and just hand them these colors and say, order these without any further instruction, you'll get all sorts of weird orderings. Some people will recognize them as coming from the rainbow and pick that, but people will choose all sorts of other weird things. They may just do it randomly because they don't understand. They may go from the darkest to the lightest. They may try to alphabetize them. It's really unclear what people will do, because even though there's a physical ordering of these colors, there's no sort of natural ordering, from our perspective of what that means. And so anytime you look at colors like, the different hues of the rainbow, there's this sort of cognitive process that has to go through. We have to remember that green is in the middle and red is on the top, because we arbitrarily say red is on the top, blue is on the bottom. Okay, I see a loaded question from Alan Scott. There's more resources for good color maps. Any websites you'd recommend? Yeah, there's a loaded question because I have a website, I have a page on my website that collects resources for colors if you want to learn more information. So I'll go ahead and post that to the chat as sort of a self-aggrandizing suggestion. You're welcome to kind of peruse that, and I don't claim that the page that I have is particularly useful. The most useful part about that is I have links to other pages as well that has more good color advice. Things like Color Brewer is a great resource. There's a link to the Psi colors that are done by the group at Los Alamos, that they have a lot of expertly designed maps, with many of which are in Paraview, as well as things like Color Moves, which is a separate application to help you design color maps. It's a lot like the color map editor in Paraview. Well, the Paraview is just pretty basic. They have some more advanced color editing tools and things of that nature.
So we should probably try to move on to the next video. We're getting tight for time, and we will have a lot more at the very end. After the next two videos on advanced rendering, we will have 5 minutes at the end, and then we can stay online and chat on Discord after the whole thing is over. But thank you, Ken, very much. I very much appreciate color. So we should move on to advanced rendering techniques.
Good morning. My name is Dan Lipsa. I am a developer for VTK and Paraview. I'm going to do this presentation with Michael Migliore. He implemented some of the features presented next, and also he worked on the visualization I've shown on this slide. We're going to talk about advanced rendering with Paraview. So I'm going to start with an introduction, and then I'm going to cover two parts: physically based rendering and ray tracing. We're going to have a short break between these two parts for questions. So the main visualization goal is to gather insights from simulation data or real world data. A secondary but very important goal is presenting your data to an audience. An appealing visualization can spark discussion, engage an audience, and generate funding. So we're going to cover tools and techniques borrowed from computer graphics that enable you to build a more appealing visualization in Paraview. So physically based rendering is a rendering technique that generates visualizations that are more realistic, and also there is a more intuitive way to specify rendering parameters. So whereas the classic rendering, Gouraud, uses specular, ambient, and diffuse lights, PBR uses diffuse light, roughness, and metallic. I included this reference that has a good description of the theoretical information about PBR and also it has shaders for OpenGL. So in this presentation, we're going to cover a number of short examples that will allow you to practice turning on these features in Paraview. So we're going to start with this torus example that is rendered using PBR. So you already went over basics of Paraview. So what we're going to do is generate a torus, increase the resolution, set the lighting, the interpolation for the torus to be physically based rendering, and set the torus to metallic, and also set the color to this orange color. Yeah. And then we can play with switching between flat interpolation, Gouraud, and physically based rendering. And also we can color the torus by a scalar, either with metallic property or non-metallic. Yeah. So let's do that in Paraview. I'm using Paraview 5.8. You could use 5.8.1 or even the latest master. So we're gonna start to create a torus. So that's super quadric. I pressed Control Space, super quadric, and then set the resolution to 64. Apply. Yeah. And then set the rendering. So that's in the display section. Make sure you set the advanced properties here. Lighting interpolation, yeah. So we set that to PBR. Notice the rendering changes. We can turn up metallic. Can turn down roughness. Notice the spots, the highlights are decreasing, and they're gonna disappear completely if it's a completely shiny material. And then we can change the color. This is edit color map to this orange. Yeah. So this is the torus we wanted to get, and then we can play with flat rendering. Can turn on the specular light. So notice in this case you have one color per face. Yeah, because you have one normal per face. Case of Gouraud shading, the color is computed in each point and then it's interpolated along the face. For the PBR shading, you have more complex lighting computation, but more realistic rendering. You can also color by a scalar and Z coloring. If you turn down metallic, you're gonna have this dielectric material, this non-metallic material. Yeah. Can turn on roughness, the spots disappear. Okay. So in the previous example, we specified parameters using just one value. You can also specify these parameters using a texture. So we can use a texture for color, roughness, metallic, luminosity. And additionally, besides these standard parameters, we can use a normal texture. So for the normal texture, this perturbs the normal vectors to show more features in the model that are not specified using triangles. So you see this roughness in this cube and also the writing. So this is just a regular 6-faced cube. but you see all these features that are not specified with triangles. Occlusion mapping, it's a technique that specifies areas that receive low indirect light to accentuate perception of cracks or folds in the model. So the left side has occlusion mapping, the right side does not. Notice the cracks are more visible in the left model. So we're going to look over an example to show how all these textures are applied to models. So for this, we're going to use a model downloaded from this website. These are free models that you can get from the Kronos Group website. So what we're going to do is first we're going to enable the GLTF reader. This is a plugin in Paraview. And then open the water bottle that's specified as a GLTF model. Turn on advanced properties and set the normal texture. You'll see we will need to flip the textures to cover correctly the model, and then we're going to set the color texture. Okay, and then so all this stuff is applied to, so all these two textures are applied to Gouraud shading. These work here as well. The next two textures work only for physically based rendering. So we're going to set the occlusion, roughness, and metallic. That's just one texture, and then we're going to set the emissive texture. Yeah. So let's do that. We're going to reset first. And then we're going to tools, manage plugins. We're going to load the GLTF plugin. Select GLTF reader and then load selector. And then close. And then open from the tutorial materials folder. Open the water bottle GLTF. And then apply. Yep, so this is just the model. Now we can apply the normal texture. This is in display properties. Normal texture, load, inside water bottle. This is the water bottle normal, PNG. So you already see something is showing up here. You can play with the normal scale. Yep. But as you can see, the texture is not applied correctly. So you can check this checkbox, flip textures. And now the texture applies correctly. So there are two standards. You can apply the texture either from upper left corner or from lower left corner. So both are used, so you can flip the textures if the texture is not applied correctly. So notice you have roughness in the cap here, you have some patterns, you have some writing here, you have some writing here as well. Yep. Now let's apply the color texture. This is the texture property. Mix color. Yep. So this looks good. So all this is with the Gouraud shading. We can switch to PVR. Notice the color disappeared. The reason is the color texture has a different property name for PVR. So we have to load it again to base color. Yep. We still have the normal texture. And then we can load the material texture that contains occlusion map and then metallic and roughness and metallic. So let's load this. Occlusion, roughness, and metallic. Yep. So the yellow part kind of looks metallic. You have to be careful here. You have to turn on or move up the slider bars for this roughness and metallic properties, because these properties get multiplied with the texture. So if you want to apply exactly what is in the texture, you have to turn on these properties. So now the bottle looks right. And the last texture is the emissive texture. And this created, so let's rotate around the Y axis, press the Y button and rotate the model. So this created this time and temperature emissive property here on the bottom. Yeah. Okay. So if you take a look at these textures, the color texture has what you would expect, this red that gets applied on the cap. I think this is the top of the cap. You have these logos, and then you have the black that's applied at the bottom. The normal texture shows roughness and different patterns. You see the writing here at the bottom. The emissive texture shows the emissive part. The occlusion texture, remember this is packed into this occlusion roughness metallic texture. Yep, so the occlusion texture shows areas where you should have like shading, where cracks are. So this is kind of one area on this rectangular part here. Also around the cap, this occlusion is applied. And then this is the roughness part. So you see various patterns here, the writing as well. So and then the last part is the metallic texture. The metallic part has a high value. Yep, so that's the white part here, and that gets applied to the yellow part of the bottom. So next we're going to look at image-based lighting in Paraview. So or skybox. This is an alternate way to create a surrounding environment. So one way to create a surrounding environment is to model it. You can create the 3D environment, but this may be time consuming, and also it's time consuming if you want to use raycasting to render that. Using a skybox, it's a lot easier. You can create that with an app on your phone, and it renders very fast as well. So the skybox is used as a background, but also it's used to light the model. So it's used as a light source. It consists of the 6 faces of a cube. Yep, that is sort of, it surrounds your model. If you open up one of these files, one of these skyboxes, they don't look like these 6 boxes. They look somehow deformed. The reason is that the sphere gets projected onto a cylinder, and then that cylinder is unwrapped and stored in the file. So you can download many free skyboxes from this website. For Paraview 5.8, you will have to convert the file you downloaded from there, which has the extension HDR, to a PNG. You can use ImageMagick or other software. Paraview 5.9 supports the HDR format. So the example we're going to look at next shows you the torus with a background, one of these HDR images, and it shows you the torus that reflects the environment background. So what we're going to do is load create a torus, set the lighting to PBR, and then load the skybox. That's done in the backgrounds, in the background property, view property. Yeah. So let's reset the session and then load a super quadric, create a super quadric. Make sure you set the resolution to 64 so it's more rounded. Set lighting to PBR, so the lighting property, the interpolation property is in the display property, so that means it applies to a certain model and a view, so it applies to this pair. So different models can have different lightings, and also models in different views can have different lightings. So set this to PBR. Turn on the metallic, turn off, well, maybe not up till the end, of roughness like that. And then go to view properties, background, choose this skybox, and then load in the folder Autoshop 4. Yeah. So right now the background is set to this file, but still the model does not reflect the background. For that to happen, you have to check use as environment lighting. So now the model reflects the background as well, and it's lit by this environment, by this skybox. Notice you still have the spots from the regular Paraview lights. You can turn those off if you want to. I'm gonna look at this in a later example. Okay. So we're gonna stop here for a few minutes to answer any questions you may have.
So we have about 30 seconds, and we can encourage you to type your passwords, type your questions into the chat. Do not type your passwords. And then we'll have to move on to the second part of the advanced rendering.
Yes, so please ask your questions on this course. We don't have too much time here, but we'll be around to answer any questions you have on this course.
Okay, so Alan Scott asked, where is Skybox documented? We'll get Dan to answer that, and we should probably roll the next video.
Next, we're going to look at ray tracing in Paraview. So ray tracing is a rendering technique capable of producing high degree of visual realism. It supports physically based rendering and image-based lighting that we've seen implemented in OpenGL, but also it supports shadows, reflections, and refraction, and setting materials. We include two ray tracing engines in Paraview. We include Intel Osprey and NVIDIA Optics. Depending on your available hardware, you can use either of them. You can use this option in Paraview, enable streaming, which allows you to use a low resolution ray tracing when you interact with the model and a higher resolution when you stop interacting. This is still experimental, and in my experience, it only works in Unix. So we're gonna look over this example. We're gonna set up this example with the torus that reflects a skybox that we've seen previously, but also it reflects the planes that I set up around it. So this doesn't work the same in PBR implemented in OpenGL. OpenGL, you will see only the environment around it. You won't see the actual planes. Yeah, so you need ray tracing to see the planes as well. So we're gonna reset the session, load this Paraview state file that has the torus and the 3 planes set up around it, and then set PBR for the torus, and then load the skybox, use it as environment lighting, set the roughness to 0 and metallic to 1, and then last thing we're gonna do is enable ray tracing. So switch to Paraview. So we're gonna load the state file, so load state, and then torus. This is the torus with 3 planes that I set up, and then you can set for display properties. So I'm gonna set the PBR for the torus. Yeah. We don't need to see this box. Yeah. So there is a properties show box that hides that box, that interaction box. Okay, we set the metallic property to a high value and roughness to a low value. We load the skybox, that's a view property, background, and load the auto shop, and also use as environment lighting. So notice the planes are not reflected by, this is the bottom of the skybox. They are not reflected by the torus. If we enable ray tracing, you don't see it right now. Well, you see it. So this is a rough rendering because we use just 1 sample per pixel. If you set this to 10 samples per pixel, it's going to take a few seconds to render, but you will see much clearer that the planes are reflected by the torus. Yeah, you can set this back to 1 so that we can interact with this easier. We can turn off the lighting so that is view light inspector, and turn off Paraview lights, the lighting. Yeah. So this right now only the environment is used for lighting. And you can set the samples per pixel to a high value. Okay. So let's reset. Besides environmental lighting and PBR ray tracing supports shadows. So we're gonna look over this example where we can see a shadow from the torus, and also we can see this soft shadow. So to do that, we load the torus state file. We enable ray tracing. We can switch between the Osprey and Optics path tracer to see that they're pretty much identical. For ray tracing, the background is important. It is actually used as a skybox. So you'll see if you set a white background, your model is going to be washed out. It's going to be very white. So to see the model with only the lights that are in Paraview, you have to set a black background. To turn on soft shadows, you have to turn off the Paraview light kit and add another light and set the radius for that light to 10. So the lights in the light kit don't have the radius parameter exposed, so you will have to add an additional light to, try that out. So I'm gonna load the torus state file. Enable ray tracing. So you can play with the background. If you use a white background, your model is gonna be washed in light. So if you set a black background, it looks right. I already have the light kit on. If you don't have it on, view light inspector. So I already have the light inspector on. So I'm going to add another light and turn off the light kit. So now you see the shadow, that's a hard shadow. Can set the radius to 10. And that creates a soft shadow. You can, if you look in the view properties for ray traced rendering, you can switch between the Osprey path tracer and the optic path tracer if you have a NVIDIA card. And you'll see it's pretty much identical with the Osprey path tracing. You can set the samples per pixels to 10. Yeah. Okay, let's reset and look over the next example. So in this example, we show materials. So we set the torus to be one of the default materials in Paraview. It's called scratched, and we set the planes to be reflecting material. Gonna use aluminum for that. Yep. So we load the torus state file, turn on path tracing, and set a black background. And then set the torus material to be scratched, set the two plane materials to be aluminum. So let's do that. Load state, torus, turn on path tracing, and turn the background, make the background black. Okay. And then the material property, you can look through it, you can look for it. It's in the display properties. But first you have to select what you're gonna apply the material to. So it's not easy, there are lots of properties here. Material, here, yeah, ray tracing material. Easier is to just search for material. And material in our case should be scratched, yeah. And then these two planes, we want to make them aluminum. So I think this one is this, yeah. Make this aluminum. And I think this one, we need to make that one aluminum as well. So this is the the example I wanted to try out, you can increase the number of rays per pixel to 10, just to see how it looks when it's rendered nicely. Okay. So let's reset and look at the next example. So the next example shows you refraction. So this is as simple as just setting the material for this to a material that is transparent. We're going to use glass. You're going to see here there is a difference in this case between the Osprey and the optics ray tracers. So load state, load the torus, set black background, and then enable ray tracing. So right now we're gonna set the material for the torus to be glass. Yep, so you can see these lines refracted through the torus. Let's change the backend. Instead of Osprey, we're going to use optics. Notice it is slightly visible. There is a shadow as well, but not as pronounced as for Osprey. Okay, so there is a little bit of shadow. I don't know if you can see it. And change the Osprey. This is a lot more pronounced. Okay. So, Paraview has a number of predefined materials, as you have seen. Those materials are stored in a JSON file at this path. These materials are based on Osprey materials, so they refer to Osprey materials, and they have the following structure. They have a name, and then this type refers to an Osprey material name, as is spelled in the documentation. And then you have a number of parameters that override the materials in Osprey. So if you don't specify the parameters, the default ones are going to be used. So for aluminum here is just type metal with default parameters. For copper, we have to override some of these liking parameters. To define your own materials, you have to create one of these JSON files and then load it using file load path tracer material. Osprey has a number of materials. The simplest one is the OBJ material that's based on lightwave OBJ format. All other materials are physically based rendered, and one of them is the principal material. That's the most complex with the most parameters. And then you have additional materials that allow you to specify fewer parameters, but they are based on this principled material. So all the PBR materials are rendered using physically based rendering. The OBJ material is rendered using raw rendering. So this ends the ray tracing part. Wanted to also mention another backend that Osprey has. This is the Osprey raycaster, which behaves like the regular OpenGL Guru shading, but it has a few more features. You can have shadows and you can have ambient occlusion. And this is an example that shows the ambient occlusion and shadows. This is a model rendered with the regular Guru shading, and this is rendered with Osprey raycaster with ambient occlusion, so it looks a lot more lively. So To create this example, we're going to reset the session, create the wavelet source. This is an example we use for testing. Just creates a 3D data, image data. And then we shrink the cells just to create more points and apply a sphere glyph to each point. Then, so that gets you the Gouraud shading. And then we enable ray tracing, switch to the raycaster backend, set the shadows to 1, so that enables shadows, and set the ambient samples to 12, that enables ambient occlusion. So we're gonna use control space wavelet, apply, and then control space shrink, that shrinks the cells, apply. Yeah, so you have a 3D volume. And then we apply the glyphs and make sure we choose the glyph type to be sphere, and also scale factor. You have to press this recycle arrow, reset using current data values, otherwise you'll get very big spheres too. And then apply. Okay, we have to hide the shrink. So this is the spheres that I showed you in the example. This is the Gouraud shading. Let's try to see if we enable ray tracing, what happens. Nothing happens because it's Osprey ray casting, so it looks exactly like the Gouraud shading. We enable shadows, it looks a little better, and then set the ambient samples to 12. So it looks a lot better than the regular Gouraud shading. So this ends our presentation. Thank you very much, and we are open for questions.
So we have a minute or so for questions specifically regarding advanced rendering.
Yep.
Okay. So we do have one from Carl Drews, which is, how would you map grid lines onto an irregular 3D surface or shape? Which I could imagine, just off the top of my head, you can resample with data set. But I don't think that's getting to his question. So, you have any thoughts, Dan?
No, I don't fully understand the question.
Transparent background. So when you save a when you save a screenshot, I believe you have an option. There is somewhere where you have an option to make a transparent background. And I believe it's in the process of actually saving the image that you get the transparent background. And so is there a simple rendering for a working space and a high quality rendering for the final output?
You will have to see it in Paraview. So I mean, you can play with it. You know, you can do all your development using OpenGL, and then switch to ray tracing at the very end. So you can do it that way.
And how does Paraview deal with the big scene? In physical Osprey rendering for crowd scenes that are computationally complex?
So it should be similar with what the Ray Osprey or optics does. There is a conversion that happens as well from BTK representation to Osprey representation, but that happens only at the filter execution. So it should be, the rendering should be similar with the regular ray tracing.
So we will stay on Discord and try to answer more questions if they come in. In the meantime, I have shared my screen and I put all of our email addresses up there, for better or worse. I don't. And you are welcome to stay on Discord and chat with us, or move on with your life and eat lunch, depending on what part of the world you're in, or send email, which I get a lot of email, so I'll try to respond if I get some. But we thank you all for attending the Paraview tutorial, and we hope you have a fantastic IEEE VIS 2020 online, sitting at home. So I guess we can keep, well, I guess we're supposed to, I think we're supposed to be very clear that we are at an end. So my computer says it's 11:30 and we're supposed to be done at 11:30. And so we can release our technical producers here. Thank you, Sam, very much for running this. We've done I think it's, for the first tutorial, it's been good. So thank you.